One more. Specialist. That's why. That's why. I don't know. I just signed it because it is all looking stuff. Yeah. Right. What is that first? Let's say that. Yeah, final answer was more about the year. One of the people was his name, that was looking back news. Yeah. Your name. We're cleaning several paper for patients around those who numerous ground and these are several cases. So, yeah, so that was the case. Your house, four achievements from the or AIDS, the ones that we will do complaints that are fine. There was an article. I mean, this is first, but it's very good. It is. There's no like in the kind right from my back. There's no holes. Did I take our techniques? No. Oh, I see. Thank you. Мы с Дмитрием часто занимаемся перетягиванием мутьев. Как разделять круг?
Yeah, they're doing like yes. Yeah, oh, it's over like. Ну, я обычно так и делал. Если приехал,
Okay, so it's about 10 a.m. So I think it's about time we got started. Welcome back, everyone, to the second day of this summer school on Superconductivity. We're just going to pick up right where we left off, and have last with Agterberg. Continuing again the top two of this discussion.
All right, thanks. And yeah, good morning, everyone. All right, so yesterday in this whole agenda, we got through these two bits. And so what I want to do today is get somewhere around here. But let me just review what we did yesterday and look at the key results. So I showed you what the form of the Bogomolov-de Hamiltonian is in a particular basis choice. I told you there's a couple ways of writing it, but the choice we chose is the one that's the most common. And then I also emphasized the role of inversion, time reversal, and charge conjugation symmetry. So inversion and time reversal were important because they're the ones that guarantee that there is a BCS superconducting state. And so the log that you saw here in both Nikolay's and Andrey's lecture, the source of that are these two symmetries. And then charge conjugation, it was related to the Pauli exclusion principle, and it's a guaranteed symmetry of these VDG Hamiltonians. And we wrote down operator forms for these three symmetries. All right, and then we looked at the single band limit in particular. And in the single band limit, we assumed that in the normal state, we had both time reversal and inversion symmetry. And then we saw that in that single band limit, we have symmetry required nodes. So these are defined by the point group of the material we're interested in. And then if we look at the excitation spectrum, we find that there are three types of excitation spectra. Either the system's fully gapped, it has point nodes, or it has line nodes. So in here, there's no possibilities to get a Fermi surface in a superconductor. And so this is sort of the late 80s, early 90s point of view of single band theory of superconductivity. But then when you look at some experiments, it seems to indicate differences from this point of view. I told you there were robust nodes that are not guaranteed by symmetry. So we're beginning to address where those come from. There are situations where we have gaps, where we expect the single band theory gives us nodes. So we want to understand how that can occur. And then something slightly more obscure, there's a violation of Blount's theorem. And I told you what Blount's theorem is. It's the statement that in single band superconductors, when you have spin orbit coupling and it's spin triplet or odd parity pairing, you can only have at most point nodes. You can never have line nodes. But there are theories that give you line nodes. And so there's something missing in understanding this. All right, so that's the overview. Let's now go back to where we ended up. And that was this homotopic classification of nodes. And the problem here we're addressing is how do we get nodes that are not dictated by symmetry? And so the answer is in topology. And I told you, okay, we went over this slide yesterday. But what I'm going to do is tell you about one particular such classification of nodes. And then I'm not going to focus on the topology too much. I'm just going to tell you the results of the homotopy groups that come out for the space of Hamiltonians that are dictated by symmetry. So we have mappings from momentum K to the space of Hamiltonians. And those mappings we can then ask, are there mappings that contain nodes or of some sort, like line nodes, or maybe, yeah, so here's a line node that has topological charge, but here there's no topological charge. And then we can just look at the answers from topology and see what kind of nodes exist. But I'll give you some more information how you deduce whether we have nodes or not. Okay, so let's begin with that classification. It turns out this is a problem that has been done by many people. And so here's a list, and it may not even be complete, of people who have worked on classifications of topological superconductors and in particular nodes. But I choose one particular paper I follow because it's my favorite, and that's by Thomas Baduzek and Manfred Siegrist. It's published here, and I'll tell you why it's my favorite. So in all these different classifications, everybody chooses different symmetries to then use that to define their topology. But we've already talked about what symmetries are relevant for superconductivity. I told you time reversal and inversion are, because those stabilize the superconducting state. And of course, we have to include charge conjugation. So in my opinion, the most natural classification needs to include these three symmetries. But in addition, we're doing a nodal classification here. And so we're going to be interested in symmetries that keep a particular K point unchanged. So inversion and time reversal are not great, because that takes a state at K to momentum minus K. And so it's not a local in K operator. Yeah, so so what we want to do then is identify from these three symmetries, what symmetries take K to K itself. And it turns out there's three of them. First is time reversal times inversion. So we talked about that yesterday. That gives us this twofold pseudospin degeneracy. The second one is charge conjugation times inversion. I told you yesterday charge conjugation takes K to minus K. Inversion also takes K to minus K. And these are anti-unitary symmetries, so they have the complex conjugation operator in them. And then if we have these two, we have a final symmetry, which is the product of these two. And this is often called a chiral symmetry. So this is a unitary symmetry. And when we went through the definitions of these, well, we saw this, and then in full generality, you can have TI squares to plus or minus 1. We focus on the case where it squares to minus 1 for fermions. Though in some cases, it may be that the plus 1 is interesting. I wrote down a form for the charge conjugation operator and also the form of the inversion operator in particle hole space. And in particle hole space, we saw there was a difference between the even parity and the odd parity case. And that difference will show up in one of your homework questions, okay? So you have to think about that. And then, okay, the product of those symmetries are defined here. So we went through a lot of this yesterday. And again, this is an anti-unitary symmetry that can square to plus or minus 1 or not be there at all. So that's another possibility. And then finally, this is a unitary symmetry, so it's going to square to 1. Okay. Now, it turns out that these are exactly the same conditions as the famous tenfold wave for topological materials. The only difference being that the symmetries done in this tenfold way, used in this tenfold way, are different than the symmetries used here. So in the tenfold way, we were interested in symmetries that keep site local unchanged. And those symmetries were time reversal, charge conjugation, and its product. So this symmetry turns out to be the same, but these two are different symmetries in that case. But in some sense, all we're doing is asking what keeps K local. So these are our key symmetries. And so then we can exploit the results from the tenfold way and then write down all the cases that accommodate the constraints with the plus or minus 1s and then possibly not being there. So there's some, so you've probably seen this table before, but now that in those cases, the symmetries were time reversal, charge conjugation, and their product. But now I have this inversion because we want local and K states. Okay. So now I've also told you that I'm always assuming that the normal state has both time reversal and inversion symmetries. And because it has both time reversal and inversion, that means that in the superconducting state, we're going to have this symmetry of some sort. And it's going to turn out that we're going to have this symmetry where it squares to +1 and where it squares to -1. All right. And so the 4 classes that we're really interested in here, and that's going to describe our even and odd parity superconductors, are these 4 classes here. Right. And then I'll point out later that you'll look at, I think it's this class for the homework. Okay. Okay, so we're going to be interested in these 4 classes, but now how do we implement this? So we're asking what kind of nodes we have. And the first thing we do to ask what kind of nodes do we have is we try to figure out what node dimension is allowed in each of these classes. And so these are commonly called codimension arguments. And it's easiest to illustrate how we do this. And so I'm going to focus on the class D3, which is this class here. It tells me that time reversal inversion squares to -1, which we talked about. Charge conjugation squares to +1. Charge conjugation times inversion squares to +1. And that's we had talked about as well, because I told you charge conjugation is this tau x Pauli matrix. And when we square that, we get 1. And then, of course, the product of these is a symmetry. So we denote this by saying S exists. All right, so the way we do codimension arguments is we first identify what are the minimal number of degrees of freedom we need to have to describe our system. All right, and we already know that. We have pseudospin, so we're going to have Pauli matrices or 2 degrees of freedom corresponding to that. And we have particle hole symmetry, and so we have 2 degrees of freedom corresponding to that. So we're going to have 4 degrees of freedom in our Hamiltonian. So that's our minimal number of states we have. And in the homework, you're going to be asked to think about this in some cases and make a decision on the minimal number of degrees of freedom needed. And in one homework problem, it's not going to be the same as this. Okay, so we know what our minimal Hamiltonian is. It's going to be some set of coefficients times Pauli matrices in spin space or pseudospin space and particle hole matrices. Okay. Now, what we need to do is we need to implement all these symmetries, but we've already seen how to implement them because we saw some of the algebra yesterday. Okay, these are the symmetries rewritten. So here we need to choose a charge conjugation, a time reversal, and a chiral symmetry. But our charge conjugation is going to be exactly what we wrote down last class. It's going to be tau x times complex conjugation operator, because inversion was trivial acting on this particular state, because this turns out to be an even parity state. And then our, oh, that's strange. Okay, oh yeah, time reversal times inversion is just going to be the time reversal operator we wrote down yesterday as well. And then finally, I should have put a tau 0 here, but okay, I didn't. And then finally, our chiral symmetry is the product of these two. And that's just by multiplying Pauli matrices, we get this. Okay. All right, so we have these 3 symmetries, and now we're going to impose these constraints on this Hamiltonian. And so what I thought I'd do to make it explicit is just do that on the blackboard, since it's not useful really to do algebra like this. But let's impose those constraints. Actually, I'm going to drop the K index because everything is none of these symmetries change K, so there's no point in keeping it. All right, and so the first symmetry I'm going to impose is this chiral symmetry. Which is tau x sigma y. And it's going to have to produce minus the Hamiltonian. So the only terms that are allowed in this expansion are terms that anti-commute with this chiral symmetry. So I want to ask what operators in this space anti-commute with this, and I can start writing them down. So I will write them down, and you can check that these all anti-commute. So sigma x and sigma z anti-commute. So do tau y and tau z. But then I can also multiply sigma x and sigma z by tau x. I can have tau x sigma x and tau x sigma z. And similarly, I can multiply these two by sigma y. Yeah. And I get 8 operators that anti-commute. So this symmetry constraint has taken our space of 16 operators down to 8 operators. But now what I'm going to do is I'm going to invoke time reversal symmetry. But I'm going to use that I know how the spin operators sigma x, sigma y, and sigma z transform under spin. I know that time reversal flips spin. So it's going to pick up a minus sign for all of those. And then in addition, I need to understand how time reversal operates on the tau matrices. And here, the only thing that matters, okay, I should add the tau 0. The only thing that matters is this complex conjugation operator. And I'm going to have the matrices tau x, tau y, and tau z. And because I'm taking the complex conjugate, what happens to tau y? Flip sign, that's right. But tau x and tau z stay the same sign. Okay, so now I need my Hamiltonian to be unchanged under this symmetry. So I need them all to be even under time reversal. And so right away we can ask, is this even under time reversal? It's actually not, because under time reversal, the Pauli matrices flip sign. It's like spin up goes to spin down, right? So this is out, this is out. Is this even? So what happens to tau y under complex conjugation? Picks up a sign, so it's not even, it's odd. And then this is allowed. This is unchanged by complex conjugation, so it's even under time reversal. And then here, is this even?
Yeah.
So sigma x is what? Even or odd? Odd. Tau x is even or odd?
Even.
So this product is odd. So this is not allowed. This product is also odd. So not allowed. This product is allowed because this is odd and this is odd. So the product is even. And then finally, is this product allowed? So this is even or odd? Odd. And this is even or odd?
Even.
So the product is
Odd.
odd, so it's not allowed. Yes. So this tells us that imposing those constraints, our Hamiltonian takes the following form. It must be, okay. So I'm going to write it in a form that is more physical to us. So our Hamiltonian is described by 2 degrees of freedom. And even though I had arbitrary parameters Cij, if you relate back to what we did last class, you can see that this component is really the normal state dispersion, epsilon 0 of k. And this component is the gap function, delta of k. So this is an even parity gap function. And now we know what the dispersion relationship for this is. So we can square the Hamiltonian. These 2 matrices anti-commute with each other. And because they anti-commute with each other, in the square, there's no cross term. The cross term cancels, so it's going to be this squared plus this squared. So our quasi-particle dispersion okay, actually, I should probably do this. This makes more sense. Is this. And so what we find from this is only 2 of these parameters are allowed in the theory. And so in this sense, the codimension is 2. We're living in a 3-dimensional space. And so this tells us that we have two constraints. This needs to be 0 and this needs to be 0. Those two constraints define surfaces, and those two surfaces can intersect on lines. And so this tells us that this particular class allows line nodes. Okay. So we have those two functions are non-zero. That's our dispersion. So this has codimension 2. We have 2 degrees of freedom that define our zeros. And so those give us only line nodes. Okay. Right. So everyone's clear with that? We have one constraint gives us a surface in momentum space. Another constraint gives us another surface. They both need to be true. So those surfaces need to intersect. Those surfaces will intersect on a line. So this class allows line nodes. And we can do the same thing for then all of these classes here.
Question.
Yes.
Sorry, why can't we have the situation when like two surfaces completely coincide?
Okay. So this is related to a comment made yesterday by Nikolay. We want something that has sort of a finite measure in our space. And the fact that the two surfaces coincide is a very low, is not a finite measure. It's a 1 point in the possible set of all these functions that describe the two surfaces. Okay. Oh yeah, and then like I mentioned, this class, it actually breaks inversion symmetry. So this symmetry isn't there, this symmetry isn't there, but chiral symmetry still exists. So time reversal times inversion is present. Time reversal times charge conjugation is present, sorry. And so one of your homework questions will be to look at this class here. And actually, I already have the homework question up here. So the homework is to basically repeat this kind of argument, but do it for the class C2. And this class C2 is spin triplet with time reversal symmetry. So it's just the spin triplet version of this. So you're going to see what changes. And you'll later see that this class has no nodes. And then the second problem will be to apply this to this class. Okay, I think I have a typo there. Oh no, A3 is right. To apply it to the class A3, this is broken time reversal with inversion. And here I mentioned that you need to be careful in choosing the minimal number of degrees of freedom needed to describe this. This example will have a different minimal number of degrees of freedom than the previous case. Okay, so you see how we get what kind of nodes are allowed? In essence, yeah.
This was just the normal state, Hamiltonian, right?
Sorry?
This was just normal state.
This?
Yeah.
No, this is the BDG Hamiltonian.
Oh, so, but we don't have the number.
Sorry, these tau are in the Nambu space. Yeah. This is, particle hole is the Nambu space.
So the epsilon naught is basically single particle dispersion, right?
Yeah, single part,
Right.
exactly.
But you're saying in other cases, this C2 or other cases, you cannot write it this way or what?
Yeah, so in this particular problem, we have time reversal and inversion are symmetries both outside and inside the superconducting state. And so when we think about the number of degrees of freedom we have to have Nambu degree of freedom, particle hole. So we have 2 degrees of freedom there, and we also need to have pseudo spin. And so we know a minimal model has 4 degrees of freedom.
4x4 matrix then.
Yeah, exactly. And that's captured by this product of Pauli matrices. Okay, so we can now go to, you understand how in principle to get what kind of nodes are allowed. And so now what I'm showing you is the answer after the full topological classification for the 4 classes we're interested in. And so here's the example we looked at. We found that this has line nodes. And if you look at the homotopy classification for the particular space, you can show that indeed there is a topological invariant which can be quantized to 2 times an integer. And that's what topologically protects these particular line nodes in this case. And in these problems, these line nodes come from this chiral symmetry, which is this time reversal inversion times charge conjugation inversion. So loosely speaking, you may or may not have seen this, but when you have this symmetry, you can write your BDG Hamiltonian in a purely off-diagonal form. And then on that off-diagonal form, you can treat the off-diagonal block and define a topological index in that block, and you can show that that's a winding number that will allow you to get nodes or not. So the nodes may or may not exist, but that winding number is 2z. And here it turns out that this number 2 actually corresponds to the fact that we have basically spin symmetry or pseudo-spin symmetry. We have a double degeneracy both above and below inner quasi-particle spectrum. And this double degeneracy is captured by this factor 2. And then z, if you look at one spin species, would be this winding number as we wind around. Okay. So the information you know how to get is that there are line nodes. What topology tells us is what kind of topological classification they have. And I'm not going to do too much about that in these lectures. Okay. Okay, so that was the first example. And this actually already explains how we can get nodes not protected by symmetry. All we need is these time reversal inversion and charge conjugation, and then we're guaranteed the existence of nodes by topology, okay? And so that explains where these nodes can come from in the case of when we have so-called accidental nodes. Okay. All right, so that's nice. Okay, maybe before I do that case, okay. So this is your homework, and in your homework problem, there are no nodes allowed. Okay, so we'll see that later. And then we can, in a spin triplet case, break time reversal symmetry. And then it turns out there are point nodes allowed. This is akin, so yeah, this is akin to Blount's theorem, but these point nodes are protected by a Chern number. And so in practice, you calculate the Berry curvature, and then you integrate the Berry curvature on a surface. And if the node, that node will have some integral number classified by the Chern number. And so associated with this Chern number are surface Weil arcs, because these will be Weil points. And then associated with this index, there's a winding number that I briefly described to you, but this gives rise to flat band Majorana surface states. So on a surface, you'll have a flat band state, so non-dispersing. And that's guaranteed by this symmetry. And then here I've also written down some representative gap functions for each. So here's the D wave gap, though I could have written this one down as well. And that is protected by this invariant. I'll talk about this in a second. We've already talked about this state a little bit, but here is a standard spin triplet state, this helical state, and you can see that kx squared plus ky squared, as long as is the gap size, and as long as you're not at k equals 0, this is fully gapped. So this state is fully gapped, showing you that there are no nodes. And then there's this state here. Sorry, yeah, this state here it actually has point nodes when kx equals ky equals 0, so along the z-axis. And those carry a Chern number of +1 and -1 on the top and the bottom. Okay. All right, so now let me turn to, yeah.
Quick last question. Yeah, sorry, let's cut off. This is wonderful when everything is expanded at small k. When you put d wave as k squared minus
Yeah.
Suppose you're in the lattice.
Yeah.
Question specifically about flat back.
Yeah.
Are they flat in this situation if it's cosine functions rather than?
They are. Yeah, so you will always have these flat bands, and so you can define a surface topological invariant, which, yeah, I have to think about to define again. But as long as, so you may know this process, but loosely speaking, you project nodes onto the surface. And as long as you have some charge, so if you have one node and you go from above it to below it along the surface, then this surface topological index changes by 1 or 2 here in this case. And so it guarantees that you will have these states even in periodic lattice. Yeah, okay, so this this homotopy group characterizes lines. This homotopy group characterizes points. And so then I've also written down this group pi 0. And you might ask, what does this characterize? Well, this characterizes Fermi surfaces. And so here's the key surprise to me that comes from this analysis. In this class here, where we have superconductors that break time reversal symmetry, this tells us we're allowed to have Fermi surfaces in the superconducting state. Right, so these are Bogomolov Fermi surfaces. And what we're going to do next is examine this in detail. But this is clearly different than what we got from the usual single band argumentation we had before, right? I told you we had fully gapped point nodes or line nodes, no Fermi surfaces. But here, actually, this tells us we should have Fermi surfaces. And then as an example, here's a state that we looked at. If you remember, that had point nodes on the top and bottom of a sphere, and then a line node around the equator of a sphere. And so this says that we shouldn't have these point nodes, or at least this line node, but we should have a Fermi surface. We can still have point nodes, but actually this is a little bit subtle here. So I won't really discuss this 2Z. It turns out we have Fermi surfaces, but those Fermi surfaces are classified by two indices. And if you have a closed Fermi surface, then that Fermi surface, if you put another surface around that and integrate the Berry curvature, you can find that this is quantized as well. So it's a doubly charged topological defect, but I'm not really going to dive into that. I'm going to focus on this here. Okay. So that's the result of the topological classification. And so now we're moving, yeah.
Is this classification somehow assuming SU2 spin symmetry, or it's independent of that?
Sorry, was that?
So is SU2 spin symmetry somehow assumed here, or it's this classification is independent of that?
The only thing we have is,
Repeat the question.
oh,
please.
okay, yeah. So is SU2 spin symmetry assumed here, or is it not included? So it is implicitly included because, sorry, it's so SU2, you mean full spin rotational invariance in the Hamiltonian? No, spin orbit, even though it doesn't look like it's obviously included here, is actually included in principle. So the place it's included, and it is actually subtle, is in, for example, the spin triplet states. The fact that I take this x hat kx plus y hat ky, I've linked the spin degrees of freedom and the momentum degrees of freedom together. So spin orbit is what dictates this. If I don't have spin orbit, I can't say I have this particular combination. So it is included, but it is a bit subtle because we have time reversal times inversion. So our Hamiltonian in the normal state is proportional to the sigma 0, the identity matrix, and that has that full SU2 symmetry. Okay. All right, so.
Daniel, there are several questions here.
Okay, yeah.
I have a quick question on the Z2 classifications there. It doesn't means there are two all distinct from the surface, right? If a classification is trivial, but still means that just one kind of Fermi surface. Just saying, if the topological classification is trivial, does not mean it does not exist at the surface.
Yeah. Okay. So you're asking we could have a trivial topological invariant and then maybe still have some kind of non-trivial node.
Because the fundamental group is 0 does not mean it's nothing. Just saying you have a single identity element in that group.
Yeah. So in principle, yeah, you can have nodes that are not topologically protected, is what you're saying, right? Yeah, and in principle you can, but here we know that these nodes, when we get them, are topologically protected. So that's a good point. But in practice, all the nodes we've seen so far can be understood in this framework. And there were other questions? Yeah.
Can I have some Lodo link or some weird
Okay.
topology, like will you consider these sine and cosine functions instead of the small k?
In principle, you can, but that doesn't really appear here because I'm doing local and K physics, right? And so links usually involve looping around each other. Yeah. But you can also, like in this list of authors I showed you, people have thought about that.
Okay. Thank you.
Okay. All right, so now let's explore where these Fermi surfaces come from and what we missed in the single band analysis before, okay? All right, and then I'll tell you a little bit about that Z2 invariant, okay? And so this next part is more like, it's going to go a little bit more quickly. I'm going to give you the main ideas, but not do as many derivations. And that's because I want to get to some things that I think that you guys can use as tools effectively. So I'm purposely going to go more like a seminar style talk in this part, but hopefully pedagogical enough that you can follow it. So the main result is that if you look in a clean, even parity multi-band system, then your superconductors that spontaneously breaks time reversal symmetry, so like this KZ, KX plus IKY state, we call that spontaneously breaking time reversal because the superconducting state breaks time reversal, not the normal state. Then you find that the excitation spectrum is either fully gapped or it has topologically protected Bogoliubov Fermi surfaces. So this is very different than the single band case where we have fully gapped point nodes or line nodes. Those point nodes and line nodes no longer exist. Right? And how do we understand that? Well, we can imagine the single band picture. Here's this KZ times KX plus IKY state. So these 2 point nodes and this line node. If we go to this multi-band system, we find that these nodes become, loosely speaking, inflated. And so this becomes like a disk Fermi surface, and this becomes a torus Fermi surface. Okay. And so, okay, I mean, my main reason for introducing this is to motivate why multi-band physics can give us something different than the single band limit. But it's useful to know that there are materials where this is likely to be relevant. There aren't many great observations of these Bogoliubov Fermi surfaces yet. And typically the reason is that the density of states of these Fermi surfaces is small. And so it's not easy to pull out, but there are some good materials. My favorite is this material with thorium doping. I think this has good evidence for Bogoliubov Fermi surfaces. And I'm trying to get my experimental colleagues to look at this again more closely. And they are, but they say there's sample issues and they have to take care of that. So, but anyhow, so here's one example of a material where you think, okay, the superconductor possibly breaks time reversal symmetry. And here's polar Kerr measurements. So you shine light and then some polarized light, and then you reflect it, and then you see that the angle of polarization has changed. And you can see that as you go below the superconducting transition, you can see if you have, you can see that this Kerr angle changes here, and then you can also train this Kerr angle by field. So you apply the field on the plus direction and the minus direction, you can see that it switches sign. So this is taken as evidence that this is a broken time reversal superconductor. And so the model I'm going to use is to look at something like this KZ, KX plus IKY state that I showed you before, and people believe that's relevant for this material. But I'm going to do it with not usual spin 1/2 fermions, but I'm going to do it with spin 3/2 fermions. Okay, so I'm going from a 2-fold degeneracy to a 4-fold degeneracy. All right. Okay, so what I need to do then, yeah.
There are way to extract if there is Bogoliubov Fermi surface, let's say with line nodes, that there will be some scaling of the penetration depth. Like, is there some experimental proof?
So you're asking, can you do experiments to measure these Bogoliubov Fermi surfaces?
Yeah, so if we have line nodes, for example, then I think penetration depth is linear temperature, right?
Yeah,
Is there
yeah.
something similar for?
Yeah, so you can in principle, so you'll have a penetration depth that's like a normal metal, right? That's how you imagine these Fermi surfaces. They have properties, yeah?
And specific hit should be linear in T.
Yeah, exactly. For the line node, yeah.
For Bogoliubov Fermi surfaces. It's just a normal metal.
Yeah. Okay. Maybe I'm forgetting right now, but I thought for, oh, you're right. Your people plot lambda over T and find that's linear T. Yes, I was just in my mind thinking, yeah, thank you. Yeah, so that is the answer. Okay, so I said last class I wrote down, oh, more questions, yeah.
Why we are using like, or looking at compounds that are J equals 3/2, 5/2. Do you need like spin over coupling? Is that
Yeah.
why we're looking at not like a half?
Yeah, so so we do this because we know how to formulate everything this way, so it's a good model to use. But in practice, in these materials, spin orbit coupling, especially in heavy fermions, is very strong. And so instead of using the usual orbital spin decomposition, you need to use total angular momentum. And if the system has sufficiently high symmetry, so in practice that means some kind of cubic symmetry, then you do have these kinds of representations, J equals 3/2 in particular, something like J equals 3/2. So, but here we're doing it because this is a good way to show you how we develop the full BDG Hamiltonian and then get where these nodes come from. Yeah. So that's the idea. Okay. So, yeah.
So are you saying that this 3/2 fermion picture is equivalent to this sigma times tau thing? Like, because they both are 4×4 Hamilton?
We'll come back to that. So so in the end, yes, I'll show you how we can link back to that and how in the classification we can get these Bogdanov Fermi surfaces. But right now I'm going to a multi-band system because I need to go to the multi-band system to explain where the missing terms are in that particular Hamiltonian.
So multivariate and each fermion has 3/2 spin. Is that correct?
As what?
So like you have two bands,
Yeah.
and within a band, each fermion has 3/2 spins. Is that the
Yeah, so it has 4 components, so 4 spin degrees of freedom, and the eigenstates are linear combinations. But I'm actually going to just now go over that exactly. Okay. All right, so I need to specify what I called Hn in my Bogdanov Hamiltonian, and I also need to specify my delta, right? And then you have the full BDG Hamiltonian. And so right now I'm going to tell you the normal part, Hn. Okay. And so here we're keeping it simple. So we're using the so-called Kohn-Luttinger Hamiltonian, but this is even simpler than the Kohn-Luttinger Hamiltonian actually. And so we're going to assume a 3D system. This actually has spherical symmetry, so very high symmetry. So it has a normal k²/2m dispersion, and k is kx, ky, kz here, the vector. And then we have a parameter beta where we have an inner product between momentum and this J equals 3/2 matrices. So this is kx, jx plus ky, jy plus kz, jz. And then here's the explicit form of jz. Okay. So our normal state Hamiltonian now has these 4 degrees of freedom. And so, but we understand it because we understand the symmetry properties of these J's. Okay. So it's not so hard to diagonalize this Hamiltonian, and you find because we have time reversal times inversion, all bands remain doubly degenerate. So we have some sort of pseudospin. Well, right, that pseudospin is a little different than usual spin. And one of the cases it's very different. One of the cases it's like usual spin. But in the end, we just get this diagonal part plus or minus beta k². And so we get 2 bands. And in practice, from these 2 bands, we get 2 possible types of dispersion, depending on the relative size of beta compared to the mass. We either get 2 bands that disperse up, or we get 1 band that disperses up and 1 band that disperses down. Okay. We're going to focus largely on this case here, because in this case here, I can do perturbation theory on this band with respect to this band. Okay. And so because of that, we'll be able to understand what's going on here. Okay. Though it turns out in practice, this is the better situation for seeing Bogdanov Fermi surfaces. All right. So you have an idea of the normal state Hamiltonian. And now what I need to do is define the Bogdanov Hamiltonian. And here, this is the part that goes maybe a little bit too fast. But I'm going to have on-site J equal 3/2 pairs. And I'm going to assume that the site exists at a center of inversion symmetry. And if it exists at a center of inversion symmetry, the only possibility to make on-site is an even inversion state, right? Odd inversion states have to vanish at a site of inversion symmetry. So we're going to assume that we only have an even inversion state. And I'm going to have to make these pairing states from 4 states of total spin 3/2 at k, and another 4 states of total spin 3/2 at minus k. And so I'm going to be looking at the direct product of 3/2 cross 3/2. So this is like our usual angular momentum relationship. We know 3/2 cross 3/2 gives us 3 plus 2 plus 1 plus 0. But it turns out these states are odd parity. These states are even parity. And so what we get is a total antisymmetric wave function, which is akin to the spin singlet we had before. And that's actually explicitly written as this state here. Okay. And in fact, okay, and then in addition, we get this total j equals 2 state. And this j equals 2 state, well, you've seen j equal 2 states. And so this will have m, varying from -2 to +2, and we have 5 states. Right, so we have 6 possible local Cooper pairs we can make from this. And in those 6 possible local Cooper pairs, I'm going to make a choice of a particular case, and I'm going to spell out what I've done here. Okay, so first let me relate this to what we've done before. So here is our usual, this is akin to the usual spin singlet. And I can write this out in a matrix times all these particular states. So starting from, plus 3/2 to minus 3/2, and then just writing down the appropriate matrix elements as we go here. And then I know there should be some scalar, so I write it as delta 0. But I also told you that in this, our choice of the BDG Hamiltonian, we often have this unitary part of the time reversal operator appearing. This matrix is exactly that unitary part of the time reversal operator. So in the single band case, this was just I sigma y -1 plus 1. Now it's a bigger antisymmetric matrix like this, but we can denote this as the unitary part of the time reversal operator. So now I'm going to move from that j equals 0 space to the j equals 2 space. But I know that when I write my gap function, I should pull out this unitary part of the time reversal operator. So I'm going to do that. But then I'm going to impose the symmetry I want. And the symmetry I want is something like a kx kz plus I ky kz state. And if you look at this, this is spin 3/2 jx times spin 3/2 jz plus its reverse order. And similarly, this is JYJC. So this looks like a KX KZ plus I KY KZ state. It shares the same symmetry as that. So here's my gap function in the BDG Hamiltonian. It's going to be this matrix times this unitary part of the time reversal operator. Okay. So this generalizes what we were doing last class. And so now it's just a matter of writing down this Hamiltonian, finding its eigenstates, and seeing where the zero energy eigenstates are. So I'll tell you the answer. And I've already shown it to you. You find that what we thought were point nodes and line nodes get inflated to these. And when we were first working on this problem, we were actually interested in these j equals 3/2 systems for other reasons. And we were doing calculations that were not just simple density of states calculations or looking at Fermi surfaces. So they were normal. We were looking for edge states. And we had this persistent problem that we always found that we couldn't get rid of bulk states in our problems. So there are always these low energy bulk states, and all the scalings seemed wrong. And it turned out that's when we understood finally, after looking at it for a while, that we had these Fermi surfaces in the normal state, in the superconducting state. And so it tells you that you can look at a problem from a completely different direction and realize numerically something is amiss, and you might think it's just some numerical error, but it wasn't a numerical error. Yeah.
Why Bogoliubov?
Why Bogoliubov Fermi surfaces?
Why the name Bogoliubov is attached?
Okay, so that's a good question. So these are Fermi surfaces in the superconducting state. And so we assign to them typically Bogoliubov quasi-particles. So that's why we call it Bogoliubov. But yeah, there's some, yeah, so good question. Yeah, we first called these inflated nodes, but referees didn't like that term. Yeah.
The order parameter that you wrote in the previous slide, delta is equal to delta naught and those spin terms, that is one of the 6 possibilities.
Correct. Yeah, so the question is, the order parameter I wrote down is one of the 6 possibilities, and I think you're gonna ask more, right?
Yeah, and then the final form of delta K that you gave with the Kx, Ky dependence, that is anti-symmetric because you chose a symmetric form of the, sorry, that is symmetric because you chose an anti-symmetric form for the spin.
Yes, exactly, yes, yes.
And that is also that's also a phenomenological choice, like IKX.
It's a phenomenological choice. Just, I guess I should repeat the question again, but you asked, it takes this symmetric form because we chose anti-symmetry in the spin degrees of freedom, and so spatially it has to be symmetric. So the answer to that was yes. And then indeed, this is a choice. But you know, we do know a little bit about what, for example, phenomenological theories tell us. And I know that if I have this Jx, Jz space, Jx, Jz, Jy, Jz space, then I know that that's going to give me a 2-component order parameter phenomenologically. And I know what the possible ground states for that are. So I know the I is one of the 2 possible ground states. The other one is just Jx, Jz plus Jz, Jx by itself. So those are the 2 competing ground states. And so we're purposely choosing the broken time reversal state. Okay. All right, so now let's go, yeah.
Question. So, I think the starting point was 2U1. Yes, so you had tau. You have these 2 Pauli matrices. Yes.
Yes,
And now you really want to extend it to the full symmetry.
that's right.
That is the goal, to go to J effective 3/2 compared to that example.
Exactly. So I'm trying to show how the multiband nature gives rise to the Bogoliubov Fermi surfaces. And that's the goal. So I'm going to go back from this description to this description, and we're going to see how the Hamiltonian changes because of the existence of the second band.
These matrices Jx, Jy, they are constant matrices, or do they depend on K?
No, these are constant matrices. So yes. Yeah, so the question are these matrices constant matrices? Here, this is JZ.
Delta doesn't have K dependence, right? Or does it have?
It has no K dependence in this form.
It's still a constant, just because no momentum dependence.
No momentum dependence. So it is an on-site pairing. So I'm making Cooper pairs on-site, imagining I have some attractive U in this channel or something like this.
But at the end of the day, your energy, that E is so anisotropic.
Yes. Yeah, you'll see. I'll explain a little bit about the algebra as we go along. Yeah. But we do have coupling between K and J here, right? And so once we go to the band basis, this coupling will show up. And that, in effect, turns this into something that looks like KZ. Okay. Okay. Okay, so the numerical result is we get Bogoliubov Fermi surfaces. And so now we want to go back to exactly this basis here and understand what did we miss. So this is general. This is a good minimal number of degrees of freedom. So we should be able to deduce Bogoliubov Fermi surfaces from this. And so I'm going to go through this exercise, but I'll point out, by the way, yeah, okay, we'll go through this exercise, but there is a little bit of a loophole in terms of writing down the minimal model for this, because in the end, our state breaks time reversal symmetry. And this loophole is akin to what you're doing in the case when you have broken inversion symmetry. So formally speaking, I'm not considering the right space here, but let's just consider it and see what happens. Okay, so here we're going through the same argument as before. We're looking at class D, which has this charge conjugation times inversion. So that tells us it's an even parity state. And I'm writing the Hamiltonian in the same product of matrices. So again, I'm considering a single band here. So sigma I and tau j. And now I'm going to impose my symmetries. And the only symmetry is this one here. So I'm going to choose the same charge conjugation inversion as before, which is just tau x times complex conjugation. Okay. And I know how that acts on the Hamiltonian. It's h of k equals minus h of k. And actually, we've done this problem already, because here I did 2 steps. I first imposed, oh man, no, we haven't done that problem, sorry. Yeah, that invoked the chiral symmetry, okay. Okay, well, you can go through the same process, and then you can ask, what does the charge conjugation times inversion imply on these coefficients? And then we find that all these coefficients are non-zero, okay? And okay. Yeah, so these two coefficients we found before over here. So I had to remind myself what this coefficient was. This coefficient comes from the fact that we've in here we implicitly chose our gap to be real, but now because it breaks time reversal, has an imaginary part, and so that'll generate this tau y sigma x term. Oh, okay, sorry, I've changed my order of matrices here. So this is tau x sigma y, and this is tau y sigma y. Okay. But so we can kind of understand that, and this doesn't change any of the physics of the single band case. But these three terms are all new. And so now we have to understand what are these three terms that come from our topological classification. Well, if you go through the algebra and look at it, you realize that this corresponds to a Zeeman field, which makes perfect sense. Our superconductor breaks time reversal. And when we have time reversal, we're allowed to have a time reversal symmetry breaking field. And so in our problem, we should have some Zeeman field. This Zeeman field will depend on momentum in principle, but this is allowed by symmetry. And so what's missing in the single band case before is we never added this Zeeman field. But now we see if we want the correct single band description, we need to add this Zeeman field and ask what that does to our dispersion. Yeah.
So the Zeeman field, you said it's a function of momentum.
Yes.
It will have to be an even function of momentum, right? Because it cannot
Yes.
break inversion.
That's exactly right. It's an even function of momentum.
Sorry.
Okay. So let's go back to the two-band problem and ask, how do we get a Zeeman field out of that two-band problem? Okay. All right. So here's what I mentioned I was going to do before. And so the idea is to take our original BDG Hamiltonian and rewrite it in the band basis. And then we get two bands, one described by this normal state Hamiltonian. Okay, yeah, one described by plus, so that's this band here, and another one described by minus. And what we can do is we can treat the Bogomolov-de Gennes Hamiltonian for this as a perturbation to this because we sit at a chemical potential here. And I was almost going to give this as a homework question, but I decided it's actually not that useful pedagogically. So it's actually just a fair amount of algebra, but it's also a good way to play with the Hamiltonians so you get some feeling, but okay, that's fine. All right. So let me first discuss the structure of the single band Hamiltonian we get here in the pseudospin particle hole basis. And this is the form of it. And so if you look, you get a normal state Hamiltonian, which I described before. I described an epsilon plus. You get this gamma term, which I'm not going to discuss, but you get some deviation, and this gamma is on the order of the order parameter squared. But you also get this h dot sigma term showing up in here. Okay. But also, before I talk about this Zeeman field that shows up, let me talk about this. And so we started with this local in K state, local in space state, so no momentum dependence. But because of the K dot J coupling, this picks up a momentum dependence. And not surprisingly, that momentum dependence comes out in the single band picture to be something like Kz, Kx plus Iky. Right? And so here we get the single band picture that we expect. Okay, so that shows you how going to the band basis matters. And then we can then ask, where does this come from? And it turns out you can show that this does come from the perturbation theory. And so the magnitude of this field, I'm ignoring the K dependence, but it is K dependent, is on the order of this gap squared divided by the energy difference between the two bands. And so that is a nice small parameter. And in fact, it picks up a momentum dependence that's, well, at first approximation, it's a constant, but it has other additional terms that are consistent with the field along the c-axis. And this is, yeah.
Sorry, just let's look at. suppose I have only one band that goes up, just
Yeah.
a simple electron band. Did you say that the gap there will be constant, that there is a constant contribution for the constant term in the gap? In other words, whether kx plus iky times kz term is addition to a constant, or it's the only term in the gap that you have.
So you're asking in the single band limit, did I?
You said that there is a constant plus extra k dependence that come from the other band, or maybe. it's other-
Yeah. So no, okay, so the constant becomes this. So in the two band limit, that constant gap becomes this kz, kx plus iky momentum form in when we focus on the single band. So I'm not adding a second component, this is generated by that.
And this particular expression, psi k is what? Is what we had before?
Yeah, psi k is the
C kx plus iky.
yeah, so it's psi k and then, yeah, so it is proportional to this. Yeah, is that your question? Yeah.
You mentioned that the other case when it's like beta is smaller than 1 or 2m.
Yeah, and you have two dispersing bands upwards, yeah.
The blue extreme surface, you can see it better. Is this because the energy?
Yeah, exactly. So we expect typically deltas to be smaller than energy differences. And so in perturbation theory, this becomes smaller. And so the effective H will become bigger.
What exactly are the epsilon plus and epsilon minus?
Sorry, what was that?
What are the epsilon pluses and epsilon minus here?
Those are the two bands of the normal state. So earlier I wrote down h bar squared m squared over times k squared plus or minus beta k squared. Those are plus minus. Yeah. Okay. All right. So in perturbation theory, if you treat this BDG Hamiltonian as a perturbation to this, you find that indeed you generate this term here, and it's of order this size. And the important part is that when you examine this local pairing state in the BDG or in the band basis, you don't only have intraband pairing terms, but you have interband pairing terms. And those interband pairing terms are the one that generate this magnetic field. Okay. All right. So now let me go to this obscure thing I did yesterday, where I said, well, we can, for this particular kind of gap function, we can legitimately define a Pfaffian, and the square of the Pfaffian is the determinant. But here's the Pfaffian when this magnetic field is 0. And the important point you can see here is that this is always positive or perhaps 0. Okay, so it's 0 on the nodes, but it's positive. But now we can ask, what happens if we add this Zeeman field here? What happens to the Pfaffian? Well, we get these two terms, but we get an additional term that can now, that is negative. And so this thing can change the sign of the Pfaffian. And it turns out this is closely related to the topological invariant of this particular problem here. And the arguments I gave to tell you about the Pfaffian here also apply in this case here. Charge conjugation times inversion squares to +1, which means we can write this in some diagonal basis. And we can use that diagonal basis to make H completely anti-symmetric. And when H is completely anti-symmetric, we can define a Pfaffian. And then the form of the Pfaffian is exactly this when we look at this Hamiltonian. All right, so as an upshot, okay, let me just summarize. Because of the pairing, we get this momentum-dependent field. And here's actually a picture of that field. So you can see over the Fermi surface, it's a relatively complicated object. And this takes some work because you need to be careful to define, you have SU2 symmetry, so you need to be careful to define a z-axis and see where the spins point. But these are normal spin 1/2 directions around here. And if you look at it closely, you can see everything is consistent with a field along the z direction. But then there's also symmetry-wise x and y components that can also vary like this, and you have to multiply that by the right momentum dependence to get that. And so that's what gives you this kind of picture. But that's generated by the second band. So that second band introduces the magnetic field. And this is a little bit of help with your first homework question. So here's the answer when you have a Zeeman field and a spin singlet superconductor. This is the dispersion. you find that you get this additional contribution here, plus or minus. This is exactly like adding a Zeeman field. So this may not be new to you. But now you can see that if this has zeros, those zeros can be shifted by this magnetic field. And that's what we mean by saying inflated nodes. And so the origin of that is exactly this field that's induced. Okay. All right. And so let me briefly discuss the topological protection, which I've already mentioned. You know, at the time we were looking at this, there were already a few people who pointed out that you could have Fermi surfaces that are protected by some Z2 invariant. And you know there's a Z2 invariant, but sometimes the hard job is to identify the right invariant. And so here the invariant was exactly the sign of the Fathian. So in particular, you remember I described this surface called S0. That S0 is 2 points. So okay, maybe you don't remember, but you take 2 points, one inside the Fermi surface, one outside the Fermi surface. You compute the Fathian inside and outside. And if the product is -1, you have a topologically protected Fermi surface. And if the product is 1, then you don't. All right. And so here you can see the Fathian in this case here. Here the Fathian is positive, here the Fathian is negative, and so you have a sign change as you go across. All this really guarantees to you, okay, this should be I. All this guarantees for you is that these Bogomolov Fermi surfaces are stable to any perturbation that changes the Hamiltonian, consistent with the symmetries I started out in this particular class D. But because our invariant depends closely on charge conjugation times inversion, so I wrote P for parity, it means that there's going to be no surface consequences of that, because every surface breaks inversion symmetry, and so we can't expect this to have any relevance at the surface. Yeah, and so I'll just point out maybe one interesting result that came a little later. So if you have Bogomolov Fermi surfaces, you can then ask, can we have instabilities of those Bogomolov Fermi surfaces? And sort of a nice result that came from Owen Moon was that they showed that there is a BCS instability of this Bogomolov Fermi surface, but that BCS instability breaks inversion symmetry. So that is a nice example of getting a BCS-like instability that doesn't lead to superconductivity, but rather leads to broken inversion symmetry. So in principle, this can exist and it's a weak coupling instability. But in practice, this is going to be a very low TC event, right? If you're doing weak coupling.
Is it the same model or you need additional interaction to get this?
Maybe you need, I mean, so all I know is all interactions allowed by symmetry were added. So I don't actually know how to answer your question precisely. But yeah, the question was, is it the same model as the one we wrote down, or do you need to add additional interaction to get this? I mean, I've worked on a similar problem where we added electron phonon coupling, and then you could get it from that. But there we added an additional interaction. Yeah.
When you say BCS-like instability, what do you exactly mean?
There's a
Like
BCS log.
Huh?
There's a BCS log.
But it's a superconductor or not?
Well, it's already a
It's
superconductor.
already a superconductor.
It is a superconductor, but the instability breaks parity symmetry, and superconductivity already exists. So it's conceptually a little bit different than the BCS log giving superconductivity. Here's a different kind of BCS log giving broken parity. Okay. Okay. So that was to motivate why we want to go to multiple bands. And what I want to do is then talk about the forms of Hamiltonians for multiple bands, and I'll do that in a bit. But before I do that, let me talk a little bit about class C2. So class C2 is, 10 minutes, thanks. Class C2 is odd parity, keeping time reversal symmetry. And so we've written down the dispersion for this before. And as your homework is going to show, this has no nodes. And so we have to ask, what do we do to the theory? So I'm almost giving away a bit of the homework here, but that's fine. What do we need to do to the theory to get nodes in an odd parity state? Okay. And so it turns out to understand Blount's theorem, I mean, Blount's here just says there are no nodes, so there's no understanding. We do need to add a symmetry. but that symmetry is mirror symmetry through the z-axis. Okay, so here I'm imposing this mirror. And when I do that, I can now classify my Pauli matrices according to this mirror symmetry. And so we know for spin 1/2, this mirror symmetry is represented by I sigma z. And so if I look at my Pauli matrices sigma x, sigma y, and sigma z, I can see that sigma x and sigma y anti-commute. And so they change sign under this mirror. And so these sigma x and sigma y are odd under this mirror symmetry, while sigma z commutes, so sigma z is even. And so using mirror symmetry, I can assign symmetry labels as these are even under mirror, and this is, sorry, these are odd under mirror, and this is even under mirror. And so now what I can do is I can expand the general form for an odd parity gap function near a mirror plane. And I'm going to take the kz axis, kz equals 0 will be the mirror plane, and I'm going to choose kz as a small parameter. Okay?
So why is it ice? When this sigma z would do the same job.
Sorry?
Why did I sigma z? Sigma z would do the same.
Oh, this? Where's the I come from?
Yeah.
This is just the representation of this mirror symmetry. So, you know, it's e to the minus I. Sorry. Yeah, and so you can expand this in cosine plus I sine, and then you make theta is pi here, right, from the mirror, but that becomes pi by 2, and that gives you an imaginary part. So that's where the I comes from. Yeah. Okay, so these are odd, and this is even. Okay, so now what I'm going to do is build a gap function that is near kz equals 0, and just say I'm going to impose that the whole gap function is even under mirror symmetry because I have another symmetry. Okay. All right. And so when I do that, because sigma x and sigma y are odd under kz, they need to be multiplied by another function, or sort of odd under mirror. They need to be multiplied by kz to make the whole thing even under mirror symmetry to satisfy this constraint. So I have a kz multiplying this, a kz multiplying this, and I have some generic function of kx and ky here that I don't know much about, and same here. And then similarly, because this is an even function under mirror, there's no term linear in kz multiplying this. This will exist everywhere on the mirror plane. But the important point here is, if I now go to kz equal to 0, both these terms disappear from the gap, and I only have 1 degree of freedom left over. And so in this Hamiltonian, I have 2 degrees of freedom, but I'm constrained to a plane. And so if I have a 2D surface and I have 2 degrees of freedom, which each create a line on the plane, they can intersect on a node, on a point node. And so this constraint here allows for the possibility of point nodes on this mirror plane. And this is exactly Blount's theorem. Blount explicitly implemented these symmetries and said on a mirror plane, you can have these point nodes. Right. Now, it turns out this is not an academic exercise. And there's one material which is currently of great interest where these nodes have actually been seen, or there's good evidence that they've been seen. And that's uranium ditelluride. And so this is a recent science paper coming from Seamus Davis's group. And so what he has evidence for is point nodes protected by the same mirror symmetry I just said, here and here. This is his evidence. I'm not going to go into the details, just tell you that it's there. But this is a very nice experiment, and I'll be happy to talk about it later. Okay, and then I also mentioned, and I'll now mention again, since you know now where Blount's theorem comes from, there are violations of Blount's theorem. So this is something I mentioned before. And in this case, we can, this is actually a mirror plane, this kz pi over c. And if we want to get line nodes on a mirror plane, we need to have all 3 of these components vanish on the mirror plane. So what I wrote, when I said 2 of them are multiplied by kz and 1 is not, the argument has to change that all of them need to be multiplied by this factor of kz for this to actually occur. And so we're going to try to understand how that can happen. And again, that's going to motivate us going to these larger spaces again. And so we have two motivations to go to these larger Hamiltonians. All right. So I think I'm probably in the same situation as yesterday. I can discuss where I'm going to go now, and then I'll end up. Okay. So you can see where I'm headed. I'm going to now talk about what is this HN for systems that have multiple degrees of freedom. And I'm going to construct a couple tight binding Hamiltonians, and I'm going to go through a lot of detail in that construction so you can see the pieces that enter. And you'll see it is not as straightforward as you might think, but you can do it straightforwardly. But again, this is going to be motivated. One of the Hamiltonians I derive will be for iron selenium. And I told you in iron selenium, we have this M point at the corner of the Brillouin zone, and there are these two Fermi surfaces, which means there's two bands. And we need to understand where those two bands come from. And so here I'm throwing some notation down. We're not going to focus very much on this, but here we're going to be interested in the M point at pi on a square lattice. And I'm going to be interested in the little group of the M point. And the little group is all space group elements that keep this K, the M point, unchanged by a reciprocal lattice vector. So here, K is the M point, so I'm looking at all space group elements that keep this point unchanged by a reciprocal lattice vector. And it turns out some of these have non-trivial reciprocal lattice vectors attached. But when you do that, and then you do a symmetry allowed KP expansion near the M point, you find that you get this Hamiltonian. And we will derive this Hamiltonian first from a tight binding perspective, but then we'll just do a small k expansion near here to show where this comes from. But the thing you want to understand is, what are these tau matrices? What do they correspond to? And it turns out in this case here, in the iron selenium, there's 2 irons per unit cell. And so these tau matrices correspond to the site degrees of freedom of the iron. All right, and so I'm going to give you a way to try to understand that. And like I said, I'm going to substantially slow down. And what I'm going to use in particular are some nice lecture notes from Jennifer Cano that she did in San Sebastian. And there's also a nice paper where a lot of this is outlined, not exactly the same way as I presented there. And then there's a very close link between what we're constructing here and so-called the notion of irreducible band representations. What we're going to do is go from a real space picture involving orbitals. We're going to generate a tight binding Hamiltonian. That tight binding Hamiltonian has buried in it the symmetries at every K point. And so from that, we deduce band representations. That's the symmetries at every K point. And so you'll be able to see a link between that real space picture and that and those band representations. And I'll show that. Again, that's not the emphasis, but for people who are interested, the equations for that will be shown. And I'll do one example where we actually use that so we can understand what some puzzling features of these operators here. And I think on that note, then I'll stop for today and then open us up to questions.
Okay, questions?
You're talking about the V2 classification is specifically for 3 dimensions.
The which classification?
Well, non-trivial Fermi surface C2 classification is 3D, I guess, when you expect 3D. So do you have some comments on other dimensions?
Okay. Yeah. So, okay. Indeed, we did this in 3 dimensions. Okay. So you can. So I do have a comment.
Quickly summarize.
Oh, that's right. So we talked about Bogly-Bob's Fermi surfaces happening in 3D, and then I chose the classes for which apply to 3D in practice. But then you can ask what happens in 2 dimensions, or maybe even in 1 dimension. And so at first glance, not a lot changes, but there is actually an important difference in 2D. In 2D, you have additional symmetries that guarantee degeneracy between states K and minus K. So one such symmetry is a 2-fold rotation around the z-axis. That takes K to minus K. So now you have additional symmetries that you can introduce in the classification. It becomes much more unwieldy. So now there's actually 4 symmetries that you have to consider, which are your BCS instabilities. And we spent a lot of time looking for using these other symmetries to generate Bogly-Bob Fermi surfaces because we can enter different classes. but we couldn't come up with anything physical. So if you're interested, maybe there's still something to be found there, but we haven't found it.
Follow up on this question, but it's like a different direction. So far you looked at spatial symmetries where inversion or some combination with other charge or time reversal symmetry returns k to the like locally keeps k.
Yeah.
What happens if you don't have this symmetry? If you have like some higher spatial symmetry,
Some higher what?
some other spatial symmetry,
Uh-huh.
where you cannot do that. Like, are there some very fundamentally different effects in physics?
Well, and so this is the next question. So the question was, we focused on basically the symmetries that keep K invariant in 3 dimensions, right? And then you're asking, suppose we don't have those symmetries, but we have other symmetries in the problem. Can we say something? So the first thing I'll say is, and does the physics substantially change if that happens? So the first thing I'll say is that once we remove in 3 dimensions those 2 symmetries, time reversal inversion, we have no BCS log anymore. And so we're no longer guaranteed to get Cooper pairs at total momentum 0. And in fact, very generically, you should get pair density waves. So once you break those 2 symmetries separately, pair density waves are a very likely solution. So it will change. And then you'll have other symmetries that will constrain those pair density wave states in this case. In 2 dimensions, this has actually been examined because I mentioned there's these other symmetries other than time reversal and inversion that exists. So for example, this C2Z symmetry. And you can actually write down realistic models where time reversal and inversion are not present, but C2Z symmetry is present. And then there's another symmetry, which is, let's see if I can remember, time reversal times mirror along the z-axis. You can actually classify states of that and you can see what changes. And you can see there are some qualitative differences.
So you wrote down in the Luttinger case, you wrote down a spatially local pairing, which turns out if you go to the band basis, it involves also intraband.
Yes.
Those are energetically separated. So would that mean that would be at some finite attractive interaction?
Yeah, so, okay, so the question was, when we went from the local basis to the band basis, there was interband pairing terms. And then you're pointing out that the BDG Hamiltonian for this, the 2 bands are energy separated. And so the question, actually, I'm not sure about this next part, was what was the role of this interband pairing in that context?
Yes, you have to pair, they are not energy degenerate.
Yeah.
So stronger.
Yeah. So the pairing, so the point is that the pairing is not going to be 2 states at the chemical potential, but rather 2 states differently. Yeah. So in principle, that does happen. And in fact, that's why we treat this as a perturbation. Right. So as a perturbation, you generate this magnetic field, but we don't actually worry too much about the interband pairing part.
Okay.
If I may, I will play for 10 seconds the role of devil's advocate.
Yeah.
And move a little bit from symmetry to microscopics.
Uh-huh.
And you correctly emphasize the need for multi-band systems.
Yes.
Suppose I just take simplest example that similar to the case of iron selenium, where you have d orbitals, dxz and dyz. And I'm moving quickly to what I want to ask you. Normally, then interaction is in the form of cosine function, which you then expand and get cosine term and sine term.
Yeah.
Sine term will be exactly the ones that you use. Kx times kz or ky times kz. If you take only this term, you get Bogoliubov Fermi surfaces. But then, of course, the gains that you get in condensation energy will be rather small because of Fermi surfaces present.
Yes.
So my question is, what about other terms? Do you have a situation when there is only one pairing channel, the one that you studied, or there is somewhere in the background, there is another pairing channel, like cosine, or the case of d orbital, that would produce you conventional superconductivity, less interesting, but potentially with larger condensation energy.
Yeah, okay. So,
That's the question.
yeah, okay. So just to repeat the question, I focused on a case where I chose a particular pairing state, but in principle, my interactions could give other states, right? And then the question is, is it clear that the state that is stabilized is the state with Bogoliubov Fermi surfaces? Could some other state be stabilized? And maybe I'll simplify that a bit. So in the particular problem I had there, I had this JXJZ plus IJYJZ, but another state, and this is very legitimately something you can really worry about, is just simply JXJZ. So there you have two ground states already at Ginzburg-Landau level, so not invoking any other different symmetry channels. And you can now ask which one of those two ground states has the lower condensation energy. And usually we say the KX plus IKY type state has lower condensation energy because it gaps everything. But now I'm saying, no, this state has Fermi surfaces, and that's very bad for condensation energy. We didn't like the KXKZ state because that has these line nodes like this and like this, and so that tends to have lower condensation or higher condensation energy. And it's a valid question to ask now, do you lose enough condensation energy with the Bogoliubov Fermi surfaces that you push to the other state? And so this question has been looked at in a few cases, and you can show that the Bogoliubov Fermi surface state has a reasonable range of stability still before it loses out to this other state. But it is, this is a difficulty with doing these kinds of approaches because I never solve a self-consistent equation. I just say, let's put in this gap function and let's assume it has the highest TC. But these kind of questions can easily come up and you could just you could throw away the physics you're interested in because of this. So it's a good point.
I don't want to ruin this wonderful stuff.
Okay.
I think I saw your hand.
So when you include the mirror symmetry for the C2 class, in principle, the order parameter still should be sigma I and tau dependent, tau j in the expansion.
Yes.
But when we saw the order parameter as on the slide, I could not see the tau term.
Sorry. So yeah. Okay. Yeah. Let me go back. It's the wrong way. Okay, you're talking about this equation here.
Yes.
Yeah. So you're asking where the particle hole symmetry come? Where is it? Okay. What I did here was I said the BDG Hamiltonian is normal, delta, right? Delta dagger. Here I've only written that upper right block. So this is just delta. And so now I have to, if I put it in the BDG Hamiltonian, it is that block there. So that's where the particle, that's where the Nambu space is buried.
Yeah, why don't you go on back?
So what's the robustness of Bogoliubov Fermi surfaces under this order? Like Miles points should they have some region of stability?
Yeah, they do. Yeah, so many of the features you expect from this order for a normal metal show up in the Bogoliubov Fermi surface case. So you have measurable consequences of that. Yeah. Again, here you have to be a little bit careful because we're always dealing with unconventional pairing states, and usually disorder destroys unconventional pairing states. So you can't play with a lot of disorder. The mean free path has to always stay greater than the coherence length of the superconductor for anything real to be observable. But in that range, you do see responses similar to a metal.
Theoretically, even assuming that the pairing is still there, in 2D then localize. Like if you have a line.
Good question. I haven't thought about that. Yeah, that's a good question. Yeah, so it could fall in a different localization class. Yeah, so that's a good question. Yeah.
I think you have probably explained, but can you explain again that how you get this magnetic field?
Yeah. So the question was, how do I get this magnetic field? All right. Okay, the algebra is buried here, but I've done it all. So I can write down my big BDG Hamiltonian with two bands, and I can write it in the band basis. And so then I'm going to have one block, which is HBDG for the upper band, another block, which is HBDG for the lower band, and then I'm going to have a part here, and that part involves interband pairing. And so now what I do is I treat this as a perturbation to this. And when you carry out that perturbation, you find that indeed you generate this term in this normal part of the Hamiltonian. So Maybe the unclear step is the details of how that perturbation gives rise to that term, but that is where it comes from.
In this case, the lower band is below the Fermi surface, right? So
Yes. Yeah, so you're wondering what happens in the other case when they both cross or something, or?
yeah.
Yeah, so you'll still get the field, but you probably then always need to work in this larger basis. So we can't do this simplification then.
In that case, what, you have two Bogoliubov Fermi surface?
Yeah, you'll have multiple Bogoliubov Fermi surfaces, and you can ask questions about how they play with each other and things like that.
And also here, both these bands are at the same point, like gamma point or something, right? They're centered at the same point, right?
Yeah, these are all around the gamma point here. Yes.
They're coming from different points in the Brillouin. Will you get anything different?
Probably not. You'll still get Bogoliubov Fermi surfaces where the nodes are around those different places. Yeah.
Okay, so it's about past 10:30, so why don't we take our break, and if you have more questions, feel free to ask during the break, and we'll be back there at 11. Well, it's actually the 10th of you would choose next week. But if you want to switch to now, okay, then we can go right after. Okay, yeah, they're not grabbing. Or Kathy will grab him. Yeah, I think because he can do, but he also does the one yesterday, so I'll ask him if he's still. As he did, that was a difficult one he did. But yeah, you can take a lot
Но ТСТ при этом нет. Никаких вот гамма это не добьет.
Есть техника говорит, все без. Мне нужна сингуляр. Но возможно, то, что я сказал вначале, точка, где лямбда максимум, всегда правильно. Зачем искать точку, когда лямбда минимум? Моя отдельная гранула, термодинамическом пределе, она по-прежнему конечна. У меня есть фазовый переход. Есть, ну, у тебя есть charging energy, который больше, чем coupling, в итоге ты нормально ставишь. Поэтому видишь, у меня гранула, но она, конечно, размер. Я все прочно за ней могу. Она ведет себя как... Ну, ты говоришь, у меня есть бозонные капли, нету глобальной конечности. Я обсуждаю глобально. Капля конечного размера, а я хочу сделать динамический. Хорошо, как динамический предел остался. Мне по-прежнему понадобится. Развиваешь компанию симметрии. Я должен инициализировать симметрию, потому что каждая отдельная капля, если я нахожусь в нормальной фазе глобально, у меня частицы хорошие контуры. Глобально. По-прежнему использовать эту технику. Но структура функции грей, спектр, гамма, все будет абсолютно другое. Есть простой пример, это примерно то, как это будет происходить. Начиная с того, что я говорю, начинаем увеличивать протяжение. Oh, I think
Логарифм, а теперь я
no,
увидел большим-большим.
where's actually three power is equal to pi k square, right? So yeah, do you think
I thought it was very
yeah, so
Я начинаю понимать, хотя бы народно, что произойдет, когда у меня энергия света.
oh x but it's based from 0 to 1, which is not from
Yeah, but that's also, I think I also agree with that.
so full time data is coming from -1 to 1. So I write down from 0 to 1, so essentially
Like it's like a very, it's like an odd argument. So, okay, yeah, that might actually be where my head is. So this is.
Насколько используют
This
гамма,
is fine.
потому
So
что
this is from,
электронов теперь связано с состоянием.
This is taking
Гамма,
very small. So.
она не компьютерская, она скорее эффективный вакуум. Речь эффективный вакуум, я не знаю, компьютерская. Конечно, я понимаю. Я то, что определенная поверхность, чтобы просто разделить по физике.
So here C is constant.
Управление ощущением две частицы. Но это возникнет пользуется. Никакого отношения с руководителем. Никогда не управляющая система, потому что может быть моя температура высокая, а пользуется полностью перестраивается свет. Я думаю, что в этот момент, когда ты начнешь решать задачу,
yeah, I think it should come from about
есть гамма. Гамма содержит
Да, неприводимая.
Я уже это прошел один раз, и пройду второй. Андрей это сказал, что когда мы сделаем ведем обрезание. И будем говорить, она неприводима в а все остальное засунем преобразование потенциала взаимодействия в амплитуду растений.
You need either, in order to have one pull up and one pull down, K and Q minus K either go
Рисую гамму, мне принадлежит
outside vector.
гамма полностью irreducible в куперовском канале или гамма irreducible в куперовском канале, только если энергия меньше, чем все остальное засунем в определение гамма. Начинаешь делать, то ты вдруг замечаешь, не так же, как ты когда делаешь В-преобразование в мире, у тебя одна и та же проблема. У тебя есть инфракрасная и ультрафиолетовая расходимость. Ты от нее избавиться не можешь. Ты говоришь, да, но это ультрафиолетовая расходимость различится в амплитуде. И все, что она тебе говорит, что надо параметр двух перенормировать и сделать из него амплитуду расти. А потом уже заниматься электрическим. Сначала сделать амплитуду растения, а потом куперовское. Только ты прошел через полюс, вот в этом упражнении, у тебя появился связь, у тебя пропали фермионы, у тебя нет термоповерхности, у тебя больше не будет никогда куперовских логарифмов для начала. Они вообще никогда не появятся. У тебя теперь задача про бозон. Я думаю, что задача бозонов, если мы делаем все, что вот это делает, возможно, мы ищем теперь лямбда минимум в одной единице. У нас все лямбды теперь противоположного знака. Никакой нет. И по-прежнему у тебя есть какой-то отклик. Он абсолютно нормальный. Ты понижаешь температуру, теперь лямбда минимум падает. И вот вот что может произойти, так сказать, в этой задаче, то, что да, ты говоришь, что у меня лямбда может быть больше единицы. Ради бога. Лямбда единицы не составит. Ни одно собственное число не касается единицы, а сингуляр вот по-прежнему не сингуляр. Ну да, это бозон, если ты начнешь здесь, когда ты начнешь рисовский контраст, решать задачу, входящий переход. Шлям будет просто при помощи ПС, глобальная физическая генерация. Ты начнешь заниматься ровно тем же самым. Спонтанностью симметрии, ты будешь
I mean, I can help you, but Rod's taking the headlines.
Ты хочешь иметь теорию значения, чуть больше поправки, потом ставишь симметрию, начинаешь искать стабильность, ставишь ее. Равные единицы, это правильно, по-прежнему правильно написано. Но вся физика, которая в этом уравнении есть, она совершенно другая. ЖЖ, это уже теперь надо назвать бозоном.
Возвращаясь к Андрею. вопросу. Спускаемость философски. Каждый гранула, как проводящая.
Ты не можешь на это не обращать внимание, потому что charging energy это тоже тебя останавливает. Иначе я извиняюсь, когда джезусонские капли бесконечны. Я в том.
And then you can classify all Hamiltonians to a degree.
Появились.
Ну, я его не буду
А почему у тебя задача не глобальная?
Then you have to go from that set of matrices, which is all U2N rotations of those
То есть она
matrices.
большая, charging energy огромная, и поэтому тебе не глобально.
Yeah, TI, ignition, then you find that you get to some sub, then the harder.
Charging energy и level spacing это разные
Know
вещи.
that.
А я вообще не обращаю, level spacing не интересует.
Не интересует.
Меня только интересует, что charging energy больше, чем Джонсон Кап. То есть у тебя количество частиц фиксировано на Земле. Это как бы модель Бозы Хаббард, но с огромными чистыми заполнениями.
То есть вот мы с тобой скатились к своей модели там в T-измере, да, что в каждой
Она
грани.
не XY модель, там, ну, условно. Она имеет похожий, называется квантовый род.
Ну как?
So we're in K takes
И в ней есть переход.
and then,
Вот.
sorry.
Теперь вот я этот переход,
Line notes are allowed. Yeah,
You
the
know,
line-
two surfaces cross
Я
the
его
possible line. One is
Yeah, line notes are allowed.
это бесконечно.
С помощью терминала. Да, но
Yeah, so the line notes are allowed, yeah.
Oh.
Yeah, but that's your question, yeah. I said that.
Правда, мое объяснение,
I
опять
said-
же, тоже не интересно. Как мы называем вот это? И я это аффилировал, все, высокие энергии будут относиться ко всему, что
So quantum energy rates basically tell you the number of degrees of freedom that you need to specify the existence.
можно дать вот крутые лестницы,
Now you have to identify that minimum number of freedom, and in this particular case, it was. We found this as a dispersion, one, this is two. But the key is you need to start with the minimal Hamiltonian, and then you can identify the minimum number.
This-
And I told you, like, if you look at the example I gave
This is
here.
dispersion.
Это очень диаграммные цифры. И все, что связано
Or it's simple. Yeah, cross arrow.
Потом не теории есть.
Here. You can set a lot of non-zero charges, so obviously my code dimension is not 1, 2, 3, 4, 5, 6. But what I need to do is I need to derive the dispersion in the presence of that. And answer how many of these degrees of freedom are needed to change to give that a picture of it. And so I mentioned a little bit about how much was through space here. And so the answer isn't obvious because I chose a long space.
Я могу всегда сделать.
So here, co-dimension argument is not at all obvious. But here it's clear, because we can write down.
Вот эта теория, она
Just-
ничего
But here, you now have to add. It's full Hamiltonian, find the version for it, which is basically. Which is basically this. Then you have to ask which one of these degrees of freedom are necessary for us to get the thermal surfaces. It turns out it's 6. So this has to be this. So you have one. And so that tells you that there's just one dimension. But you know, this all comes kind of because I didn't start in the right space. It comes out much more quickly. if it goes.
Я почему не твой
No, no one, sigma 3, and then say like, oh, something of sigma is.
Yeah, this type of. So.
Альфа равно
this is
единице.
Exactly. So let's say,
очень хорошая
let's say I set term, say,
способ не
let's do 60 in my normal.
это поверхность.
Right, now if I take
I wanna write down
Красный
this
текст,
block down here.
который выглядит
And
как
that space
умное
better.
дерьмо.
I have to take
Если
minus a transpose of that.
Если речь пойдет о том, что спектр полностью перестроился, и эффективное состояние свободы является только. Я не хочу сказать, что само уравнение плохое, но оно ужасное с точки зрения нахождения ответа.
Как говорил Ньютон, ради
Okay,
правды,
so-
а не ради истины. Вот теперь я буду изучать альфа, самый большой альфа.
Или самое маленькое.
No, that, yeah,
Мне
we
нужно
usually
найти
do.
единичку.
В этот момент я дойду до ТРЦ от экрана. Да, и в этот момент, наверное, какая-то альфа у меня единица сравнится.
Я думаю, что можно подойти к какая-то теоретическая точка. Потому что чаги менеджера я не могу отменить, пожалуйста, книги в этот раз. Я, конечно, видел что-то, что не могу говорить о том, что чаги, но размер системы, конечно.
Something like that.
Yeah, something like that.
That's
But,
what.
yeah, so here, this reflects that, so here. I switch to location for Blackboard, but.
Я думаю, что эти вот
Second.
Я одну играл.
Here.
Я
all
думаю,
these vertical
ответ такой, что
C and C and zero are on the diagonal. All right, and so, yeah, so this is exactly, the Z component was exactly what I was writing down. I took permission transpose, so it's been tau Z, this is HC sigma Z.
Я бы
This is Z. So that's how you do it, just have to write it out. And see how you do it. Well, it's just, the general form is.
я хочу понять.
Minus H and Yeah, so then, plus minus.
Есть два, может быть, два варианта, которые надо чуть более
So it
правильно.
is exact.
Есть еще один. Произойдет ли что-то такое, что я решаю пройти?
Okay, so this is a subtle question. It emerges in the normal state Hamiltonian of the superconductor, the EEG part. So it's generated by the superconductor. So exactly, so you could have solved the problems, give you added computational normal state and same and then you solved it, so you would have got.
Charging energy is
Yeah, but now we're having a superconductor break time reversal, but from a symmetry perspective, we have broken doors.
Yeah.
Symmetry, so we should allow that term, but we're asking where does it end?
Глобальный. Что как понимаешь?
Then we allow electrons of band, upper band and the lower band.
Yeah.
To know which direction they go.
This is a question that takes some.
Разве я
Because the VDG has the normal part has been symmetry. You need to define what you mean by X, Y, and Z components in that. And so then you need to be careful to apply certain symmetry transformations to structures. And so you can get magnitude of H of K easily, but getting its direction is, you know, you need to do some sort of speaking gauge. And then you need to assign to that some appropriate gauge to understand its transformation.
The zero there is the pins band that's same as the.
And so after zero.
So this is just. It's not the zero, it's the band.
Я думаю, что вот это
It's different from different magnitude.
размер начнет перестраивать.
Yeah, and but this problem, it turns out to be essentially.
Недостаточно, и
So they're all the same. Yes. Yeah, it's not a different system of information.
So I just wanted to make sure that the aspect of when you're writing down we're going to write down what was allowed, what wasn't. And you just wrote down some explicit forms for the time represented reoperation. How much, so I'm kind of, you trying to say how much freedom you have.
You have a substantial rate freedom there, so
Or,
you,
so a lot of that freedom is just unitarily equivalent.
yes,
So-
so any unitarily equivalent choice would have worked the same.
Yes, and so my thinking is, there's kind of two degrees there that I'm not sure, that I don't think they're clear on. One is, so you write down the V of time squared, inverse squared, et cetera. You also, I assume, are assuming these, the user that has unspecified commutator trees.
Yes,
You know, the
yeah.
symmetry group.
Yeah, so in the end, you do, but in these cases, they happen to be fully, I have to think about that for a second, because, so all I implement is the square condition
Yeah,
in a space. And then from there, I have to check, maybe. So it's a good, yeah, so I never, to be honest, I haven't implemented that and I haven't checked if this imposes this structure behavior.
yeah,
Relationship, so I can't, I have to go back.
okay, but so my thinking was that you, so if you specify the commutator, you usually specify the symmetry.
Yeah,
Then.
yeah.
You've got enough relations to generators that everything is easy. Or you specify that it's not just a free truth, it is something specific.
Yeah,
Um,
exactly.
And then the second ingredient, and it's kind of comes into quite a number of things, number of, the size of your thing, that you're then choosing a particular representation. Specifically, and then, yeah, okay.
Yeah, so here I'm obviously trying to make that representation. The ones we've been working, minimal and the ones we've
Yeah.
seen already,
Yeah,
right, so you don't have to work in abstract space.
Yeah. and so from a system perspective, it's essentially, we were working theory into our application, but just the whether they're built for application, not including the use that use pairing, whatever, just the useful classification.
Yeah, I mean, here it's a little complicated with the anti-unitary symmetries, and you said formally with co-representation stuff, and so that adds some tricks to this, and this is why I had to think about the answer to your question.
Okay.
So co-representation here is a little different representation. You treat the anti-unitary elements separately.
Okay. But conceptually.
It is exactly. It is.
Okay.
That was another question. Yeah, we're saying those have to be plus and minus.
You're closest to that, but you go play what was I saying now?
Yeah, I saw it.
My experience is that there's actually more fun than a nothing more fun. I think it's also, we'll come back, I don't know where that. Story on, so kind of.
Yeah, I didn't plan that you will have more than one homework assignment.
Because our agreement was just one homework. Looks like you are supposed to start working on this homework day one and keep going. So the entire homework was already set, so I will not give you any extra kind of pieces. So let me remind where we stopped. So we stopped at the following point. I'm considering the model where the interaction is purely repulsive everywhere. It's simply a little bit stronger outside of some frequency range. But if you get closer and closer to zero in frequency, your repulsion and repulsive interaction gets a little bit weaker, which means I have F, which is the fraction of the original repulsion. So F is less than 1. 0.9, 0.5, 0.2, large, small, but still just a little bit weaker. And that's what you will have to solve now. For this, just because gamma is momentum independent, you take momentum integrals, what's left is only frequency dependence. And the entire equation now just simply decouples into high frequency part and low frequency part. So you can easily start solving this equation as a 2x2 matrix. You simply assume that delta has two values, one at low energies, below omega, and the other one is at high frequencies, above the capital omega. And the two are connected. So if at least one frequency, according to this graph, is above omega, it's strong repulsion. If both frequencies are below omega, then okay, we have slightly weaker repulsion. So that's the model. And that's what you see immediately in the eigenvalue equation, which I have written now in terms of high frequency and low frequency components. So if I have high frequency component, everywhere it's strong repulsion. So the sign is the wrong one. Well, if I have low frequency component to connect to the high frequency component, yes, it's still full repulsion. It is slightly weaker if I connect low frequency to low frequency. So that's how you get this 2 by 2. And the question is, okay, well, what are the properties of alpha T? And that's the homework. Yeah, I changed the sign kind of to have everything the same way as I was describing. So I added now minus here, so this is plus plus. So I suggest in the homework you just do 2 cases. One case is repulsion, slightly weaker repulsion. Well, the other case is different in the sense that, okay, high frequencies you have attraction, and then it goes away. So there is no coupling at low energies. You only have attraction at high energy. Compute TC in both cases. Compute how the eigenvalue will behave, the largest eigenvalue, how it depends on the log of T. And then simply combine the 2 mechanisms and see what you get for TC if I have gamma A plus gamma B together. So you have now 2 superconducting mechanisms, but working together. Let me now just, well, okay, I'm not solving it. You will do it. But I'll give you some properties of what you're gonna define. So if I solve this 2 by 2, not a big deal, of course, quadratic equation, nothing more. You'll discover the following. The largest eigenvalue will be always there. So you'll always have a solution which is bigger to 0. It looks like I'm going in the attractive direction. Even though my model is purely repulsive, I'm still going in the right way. You'll see that alpha T is monotonously increasing with temperature. As temperature goes down, alpha T is getting bigger, bigger, and bigger. Also looks good. No matter what I say, well, it still goes up. Well, but what you will see in the solution is that you will not always reach unity. And this is different from what we have in BCS. Conventional BCS, just one coupling constant, which is attractive. Your largest eigenvalue is monotonously increasing with log T, and ultimately you cross unity. This is BCS answer. Here we have also positive alpha. It's also increasing with temperature, but it may never reach unity. Well, this is because the solution which you will see is simply a highly non-monotonic function of log T, and ultimately it may saturate to a constant which is below 1. Well, I can easily kind of deduce this property very easily. I have, this is log between Fermi energy and capital omega. This is log which involves temperature in denominator. So take capital L to infinity, and it's much easier to solve right away. You will see the following, that alpha maximum at 0 temperature is limited by this number. So that's where you saturate when capital L goes to infinity. For this, you don't even have to solve 2 by 2. You immediately kind of get this from L goes to infinity. Well, it immediately tells you that for superconductivity, if alpha is always increasing, but never goes above this value, I better have this value larger than 1. So if this is bigger than 1, that's the condition for F to have superconducting transition. First, you will discover that, okay, there is a superconducting transition. So if the fraction, how much you drop down, so if this fraction, F, is small enough, and that's the condition, well, this number is less than unity. But so if F drops by this amount, your model is superconducting, which means I don't need attraction in bare terms. It's enough if I have repulsion in bare terms, but this repulsion is slightly weaker at low frequencies. How much weaker? That's the fraction left. Okay, 1 minus F is just the drop. Well, you immediately see that, well, okay, there are 2 interesting properties here. First, I need some critical value for F. So if I don't drop by this amount, just a little bit, maybe it's not enough, and I will never cross unity, and the system is normal. On the other hand, I can kind of consider this in a slightly different way. It's the same equation, I simply rewrite it differently. If I fix F, do nothing, well, it's the same one, but I can solve it for G, for a given F. If I fix F and I fix the log, you say, okay, well, the same equation simply tells me that I need G rho F big enough. So if you fix the shape of your potential and you make your repulsion stronger, stronger, and stronger, that's when you go superconducting. Sounds confusing, but here we are. Again, this is exact solution. So there is no argument, okay, what's missing, nothing is missing. So this is what you have for BCS type superconductivity, because I'm not renormalizing the Green's function in this model. Yeah, so if I have interactions, the shape of the interaction is fixed. I am going superconducting if repulsion is getting stronger, stronger, and stronger. If I fix the shape. So F is fixed, less than unity. Log is fixed. I'm not changing the shape and the frequency range. I have to make interaction stronger, stronger, and stronger to go superconducting. If it's weak enough, okay, this is conventional BCS. Who cares about formally? Just look at this. If G is very small, this log becomes irrelevant. If G goes to 0, I need the drop to be bigger, bigger, and bigger. And ultimately, when G goes to 0, the drop has to be almost to 0. Okay. Boskov, of course, if drop is exactly to 0, then for any G, you will go superconducting. So which means if I don't have a step-like behavior, but instead my effective interaction goes to 0 at 0 frequency, I probably will go superconducting for any coupling strength. Okay. I have to live with this. So that's the answer. Well, at the same time, you probably immediately see that, well, okay, from this equation, I'm talking about the case of the largest eigenvalue. You always have one which is bigger than 0. You immediately see that, well, the solution which I discussed always involves the change of sign for high frequency part relative to the low frequency part. Your delta solution makes a 0 when you cross the omega frequency. It's positive for low frequency, for example, but then it goes negative for high frequency. Well, just from the first equation, you immediately see that high frequency part, if alpha is positive, GL is positive, repulsion, it's minus GL delta L. And that's how everything works. Now, just you look at the low frequency part, this is repulsive, but HL now has changed sign. So if I take HL from the first equation, plug it in here, these terms become attractive. Yeah.
Do you have intuition for why strong repulsion can give?
Sorry?
Do you have intuition for why strong repulsion can give superconductivity? What's actually happening with the electrons?
The intuition, let's go back for the intuition. We already had it. Yes, first, let me show you graphs, which you probably will see in the homework. So if you solve this 2 by 2 and simply plot it, that's what you will typically see, that alpha is a nonlinear function of the log t, always keeps increasing. Sometimes it crosses 1. But if I slightly change parameters of the model and make my f small enough, in this case, probably it's the other direction. Sorry, I changed already notations. You may see that alpha just saturates. There is also some alpha bar, and that's what I will try to explain now. So there is one formulation of the problem which is difficult to predict, because imagine that you can do, suppose my model is more sophisticated and you can only do numerics. If you only do numerics and all your data are available only up to here, you may think that the model is superconducting, because you think that I can extrapolate, but the two curves are almost the same. So if your data are limited to somewhere here, you think, okay, well, maybe I extrapolate and the model is superconducting, but the answer is no. The curve is not extrapolatable. I have to do something else, and something else is the red line when extrapolation is reliable. And now to the intuition. We already kind of have it before. Recall that I was discussing you how Bogolyubov, Shirkov, and Tolmachov were trying to argue that Coulomb interactions ultimately may be smaller effectively than the electron-phonon coupling. So, which means if I compute effective coupling at low frequencies, I can go through the entire ladder summation at high frequencies and discover that effective repulsion at low energies is reduced by this log. And that's how literally to the potential was introduced. You introduce strong Coulomb repulsion, it's renormalized by the log, but to be strongly renormalized by the log, I need large G. You start with large G, and then these logs become important and you suppress. If G is small, okay, well, nothing happens. It just stays more or less the same, it doesn't drop. Well, and then you switch on the electron phonon coupling. It was totally different in origin. That's why that's how it was looking before. But now kind of whatever I call here electron phonon coupling, now for me, it's just simply the drop of the repulsion. It's related to the same value of G. So if the original value of G was not suppressed strongly, but then you drop by some amount, maybe this amount is not enough. And now I just would like to make sure that, well, okay, the two pictures are absolutely the same physics. So here I'm talking about effective low frequency coupling coming from interactions, from repulsion. It is suppressed, and that's the answer. And let me now I'll repeat this Bogolyubov argument for the Rachel-Shem model, not for electron phonon, but for my model, which is exactly solvable. So I will just do the same. I compute low energy effective coupling, which is repulsion, because I just go from low frequency to low frequency, just back coupling. It's FG. Well, but then I start doing lattice summation through higher frequency Cooper pairs. So it's bare repulsion, log between Fermi energy and my frequency cutoff. This is repulsion at high frequencies, high order, high order, high order, high order. Well, okay, well, the entire summation here is just the ladder. So I'll just add G and get perfect geometric series and subtract G. So it's the same. So this answer and this answer is exactly the same. Low frequency repulsion, and then high order lattice summation for everything related to high energy. So it's effective coupling at low frequencies. So that's how it looked like. Well, you immediately see that, well, this one can be interpreted as minus G1 minus F, as if I have effective attraction, which is just the drop at low frequency. Well, that's the answer, and it's exactly the same as we had before from the exact solution. The effective coupling is G F minus F star. If F is less than F star, you go superconducting because the sign is negative. If F is bigger than F star, the effective coupling is repulsive. You're not superconducting anymore. So exact solution and this consideration are exactly this, because just the model is more or less designed to have the two properties exactly the same. And that's the physical explanation. Well, why I need stronger repulsion? Just because the drop itself is related to the same interaction. So it's a fraction of the original. With electron phonon models, it's kind of two completely different mechanisms, but behave the same way. Okay, so that's what, yeah.
So in the limit of G going to infinity, this drop in the effective Coulomb interaction.
Almost
is
nothing.
actually- It's
Fraction is nothing.
Yeah.
The fraction is approaching 1, which means you just need a little bit and that's enough.
Right.
Which means the stronger the Coulomb interaction, the better.
Yeah. Okay.
Okay. So it's an exact solution. So please appreciate what's happening. So that's what it is. So that's more or less the explanation. So we have repulsion, which has this shape, and you interpret it as the following way. It's a repulsion which is just frequency independent, nothing, and an additional piece at low frequencies, which makes it slightly weaker. So it's the sum of the two. The first one will renormalize to smaller value when I go to low frequencies. And now the dashed line plus the blue one is together is attractive. And you go and pair. Okay, that's, yeah.
It was not a step function, but just like linearly.
Nothing changes, and that's the next slide. Step function is just for exact solutions, so there are no questions left. Okay, we did some mistake. But before I just go next, sorry, it's not next slide, but very close to. So all of this motivates me kind of to do something else. Let me say what I want to do something else. So this is the original formulation, how you want to discuss the eigenvalue problem. Low frequency, high frequency, fine. That's the original one. But then I will do the same, the following. I say, okay, I need the solution of this equation, and I would like to figure out if I can reach alpha t equals 1. What if I just do the following? I will simply leave alpha t here to exist, but here I will erase it. Again, for this formulation, I still look for the case when alpha bar t equals 1. And you immediately understand that alpha t eigenvalue and alpha bar t. Why I'm saying, okay, it's a new eigenvalue problem, because this vector, this is matrix vector, matrix vector. If I solve for delta H in terms of delta L, substituted back, this will just a new eigenvalue for delta L. Well, it's written in scalar form, but imagine that everywhere I'll just put a vector, and instead of GL, it's a matrix. But the solution for TC will be exactly the same, because the moment alpha bar t equals 1, it's the same as alpha t equals 1. So the both models say, okay, well, whether you can reach a solution where you have 1, 1 in both places. So now just if you start solving this eigenvalue problem, let's see what happens. Now I just don't have alpha t here, so it's trivial. I just express the delta H through delta L and plug it in below. Trivial exercise, and I end up with GF bar minus F. That's it. And that's more or less reflecting the physics which I just discussed. You say, yeah, I would like actually to do almost complete summation of high frequency part and introduce effective interactions and then work with low frequency part only. But the moment I just write down everything for eigenvalue at the low frequency only, I am dealing with effective interactions. So we call it implicit renormalization approach in a sense that, well, okay, if I formulate the eigenvalue problem this way, it's actually trivially solvable, including metrics and vectors, very easily, very efficient to find alpha bar t. But alpha bar t now is a very nice linear function of log. It immediately tells you whether you have superconductivity or not, because it can increase or decrease. Okay. So that's more or less a simple trick how I can manipulate the eigenvalue equation into something which is easily kind of extrapolatable to much lower temperature, even if I cannot solve for temperatures below, say, 10 minus 5 Kelvin. So that's how we compute a phase diagram when TC is 10 minus 100. A question?
Yeah. So this is very interesting, but is there some physical model, because the F at the end is linked to G in a realistic model? If you do it comes from a screen. Is there some model?
Yeah, it's coming. It's coming. Just, well, it's very realistic. Everything I'm saying is extremely realistic. Well, because Coulomb pseudopotential is everywhere for every material science calculation. Whenever people do calculations of TC in material science, that's precisely what happens.
Yeah, I was referring to going.
No, I'll just explain. So we're coming. I'm simply just trying to build some exact answers so as a reference frame, which means I cannot deviate from this reference frame because I know it's exact. So we just not speculate, but we kind of make some exact statement. Yeah, I probably made some statements for which I am not exactly sure. Alexei was asking me before, and I also had another statement about alpha equals 1. Do I necessarily have superconductivity when alpha t touches 1? Or maybe there is some way through eigenvectors or small amplitudes that alpha t equals 1, but I don't develop superconductivity. And I'll kind of touch this subject maybe at the very end, how general it is. I would say this is a wonderful tool if I have well-defined Fermi surface and TC is much smaller than Fermi energy. I think we're in a very good shape. So that's a very good tool kind of to discuss superconducting property. Call it emergent BCS, if you like. Okay, so that's how it works. And now just the practical advice, if you ever face the problem of computing largest eigenvalue for realistic models, that's what you do. Simply the low frequency part, just make it 0 frequency and momentum at the Fermi surface. Just everything is Fermi surface and just the lowest possible Matsubara frequency. Everything else, call it delta H and start solving for lambda bars. This will be kind of the best tool you have for predicting TC by extrapolating the results. Extrapolation will be easy. So really pushing the limit of delta L as small as you want. Yep.
So by setting the top alpha t to 1, are we potentially missing solutions to the?
No, the solution will be the same at TC. Well, because I have alpha t and some eigenvectors for a particular alpha t. If alpha t is less than 1, I have some eigenvector, some eigenfunction. I have alpha bar t, say less than 1, it's a different eigenvector. Because it's a different eigenvalue equation. Already kind of from here, this solution will drop a different matrix for delta L. but the solution for TC is the same, and the eigenvector for TC equals for TC is the same. So the critical gap function is exactly the same because I am solving the same equation. The moment I touch one. Again, the goal is to find TC. I'm simply saying, okay, well, doing this is much more efficient by any means. And ultimately, probably I'll do it on the blackboard just right now quickly. For this, you don't have to invert the matrix. So suppose I want to solve equation delta H as a vector equals some matrix delta H. And well, the lower part is like a source. So it's kind of some vector. Call it vector B. You say, okay, well, formally to solve this analytically, you say, okay, this is inverse matrix for 1 minus A minus 1 times minus B. That's the solution. And then I will simply plug this matrix to the second equation and have a new matrix to solve. You say, yeah, but sometimes inverting the matrix is painful because the matrix involves Matsubara frequencies to the left, Matsubara frequencies to the right. How big is the matrix? Because it involves the whole set of Matsubara frequency and all the K points. And maybe the size of your matrix is 10 to 7. I cannot diagonalize it. I cannot invert it easily. So that's how sometimes in material science, people start discretizing momentum space to the limit. They cannot use too many Matsubara frequency points because they want to limit the matrix. But the moment you limit the number of Matsubara points, you cannot do the very low temperature. And that's where some of the technicalities kind of go into solving it. With Matsubara frequencies, people now just have a discrete Lemon representation. They know how to kind of use a very sparse mesh and still being very, very accurate. Momentum space is more difficult. Those are the difficulties of inverting the matrix. How else I can find a solution? Here is my trick. So that's, you start doing iteration, delta H, iteration I plus 1 equals A. You act on the, by the matrix, you act on the average from all previous iterations minus B. And guess what? This will always converge exponentially fast as you want. Very quickly. No matrix inversion. By the way, matrix inversion will require the rank of the matrix, the size of the matrix cubed. This is matrix manipulation, so it's only square. First. And second, with exponential accuracy, very quickly you'll find the solution. This is called damped iterations. And damped iterations, I can easily prove it, they work as long as all eigenvalues are less than 1. But that's precisely what we have. I'm trying to get to 1. So my all eigenvalues currently are less than 1. From repulsive interactions, probably they are minus 9. But this is perfect. If I do iterations like this, remove the sum and just do the previous iteration, of course it will blow because repulsive interactions have much larger eigenvalues in modulus, like minus 5, minus 3. They will immediately blow conventional iteration. But damped iterations work magic. Try it. Just simply try to solve equation like this. F equals 1 minus 5F. Conventional iterations will immediately kind of kill you. Just do damped iterations and you will immediately see how quickly you get an answer which is 1/6. Well, the same applies to solving Bertasalpita equations and the rest, so it's much more general. But I need eigenvalues less than 1, but my goal is to reach 1, so which means everything will work. Yep.
So alpha bar T would be less than 1.
Yeah, alpha bar is still less than 1. I'm trying to get to 1. Once I get to 1, I declare superconductivity.
At the other one that we know at TC is equals to 1, the other one must be less than 1 is what I thought.
Yeah.
Okay.
Above TC, it will be less than 1. I'm trying to get to 1. Now, just well, the question is, okay, is this exactly what happens in metals? That, okay, well, I have screen Coulomb interaction and we can assume it's frequency independent. It will renormalize to smaller value. Again, I'm repeating it third time. And then you add the electron phonon attraction, and ultimately this picture is exactly the same as this one, and I go superconducting. So that's Tolmachov, Anderson, Morel, and everybody else. And the answer is no. All of this is totally fake. When I start doing Coulomb interactions, and I'm going to, what is the realistic model when everything is according to what I just said before? What is the realistic model? Well, we go to Coulomb interactions, and we notice that, okay, well, actually saying that Coulomb interaction is screened at all frequencies. That's what was assumed by Bogolyubov, Anderson, and it's total nonsense, because screening of Coulomb interactions is complete only at 0 frequency. At high frequencies, Coulomb interactions cannot screen because the electrons have no time to react. So that's what realistically happens to, we call it W function. You have bare Coulomb repulsion, 1 over Q squared. Well, but then because of the screening, Coulomb repulsion at finite frequency and finite momentum will be screened by the polarization loops. That's the easiest approximation we can do, which is called RPA. So the polarization given by the lowest order diagram is the product of two Green's functions, and RPA says, okay, plug in the bare Green's functions, you'll get the RPA polarization, or Linhart function at time equals 0 temperature. At finite temperature, okay, same loop based on the two Green's functions. So this is RPA. Now, if I take this RPA polarization, plug it in denominator, and I say that, okay, now W is effective coupling between the fermions. So I'm literally saying the following. Yes, how fermions can interact. Bare Coulomb interaction, sure. Well, but they can also do this. This will, of course, be infinity if I just do it naively. Then you say, okay, well, I can do better. 1 bubble, 2 bubbles, and just keep going to infinity with any number of bubbles. The sum of geometric series for all possible number of bubbles here is the W line. So that's precisely what is W. And that's what gives you screening. Without this, this is 1 over Q squared. But now just W is screened. Yes, indeed. Well, if I just consider W at 0 frequency, it is screened almost like U cover. So when momentum is much smaller than K-Fermi, that's how you screen. And this is so-called Thomas-Fermi screening momentum. We all know kind of this physics. Well, but if I go to very high frequencies, I recover the original bare Coulomb interaction because, okay, if I go to very high frequencies or very large momentum, that's not that important, but large frequencies simply says polarization goes to 0 and I recover back the original Coulomb repulsion. So that's now the picture for the screening. You have strong Coulomb repulsion at large frequencies and it's getting smaller when I go to low frequencies. Of course, the amount of drop depends on what kind of momentum you consider. Whether it's K-Fermi, typically kappa is also comparable to K-Fermi. Then the drop is maybe by a factor of 2, or much bigger if Q is much smaller than K-Fermi. You look at this picture and say, okay, why do I need phonons in the first place? This is exactly the picture. Okay, it's a smooth cross kind of change from high to low, not a step one, but this is not fundamentally important. What's important is that, well, okay, this number is smaller than this number. And remember that, well, okay, the stronger the repulsion, the better your chances for superconductivity. So that's the real picture of what happens with screen Coulomb interactions in realistic material. And then immediately you ask the question, okay, maybe this is already enough. I don't need electron phonon coupling in the first place because I have weaker repulsion at low frequencies. Any question for this? So, yeah.
Without electron phonon, you won't go to a negative.
I don't even need electron phonons for this picture. Because remember, okay, this was my exactly solvable result. Slightly, simplified, but what we were saying, yeah, you need only repulsion, which is weaker at low frequencies, and you're good. And you don't even have to drop a lot if the coupling is strong enough. And Coulomb interactions are strong. Typical materials correspond to RS equals 4 to 5. We consider Coulomb interactions kind of already non-perturbative at RS equal 1. Yeah, we have strong correlation, so it looks like I'm in a good place. So this curve is superconducting for large coupling. So maybe this curve is superconducting. But again, I told you that we have wonderful tools to solve this equation, so that's the answer. You take RPA, now just my scattering between the electrons is mediated by W, which is dynamic. And you ask the question, okay, if I consider the same gap function equation and consider coupling between the electrons by the W function, what can I predict for different superconducting channels? Andrey already discussed with you that if I am kind of in an isotropic case, you classify different symmetry channels, singlet, triplet, and then you have different orbital channels. So that's the answer. So this is two-dimensional electron gas, homogeneous. Coupling is going through this gamma, literally gamma equals W function. And we start solving the gap function equation for the superconductivity for different channels. What is CC, which channel dominate? And that's the phase diagram. So it says first, sorry.
And with this calculation, green functions are still free Fermion green functions.
No, it's also renormalized by W.
Okay.
Yeah, so interaction is by W, and they also renormalize Green's function by W. It's a la Migdal-Eliashberg. So it's really Migdal-Eliashberg scheme. Instead of phonons, you now have screened W interaction. So and that's the answer. So first, S-wave superconductivity. If we close all other channels, S-wave Coulomb interactions will give you S-wave superconductivity starting from RS 0.63. But it's not the dominant channel because P-wave will dominate for this range of RS. Then D-wave will dominate for this range of RS, F-wave will dominate for this range of RS, and you keep going. So actually we consider it a lot of scattering channels, and you ask, okay, how many? This is 1 over L. Oh, wait, I guess we went all the way to L equal 10, and there are no even names for it. I have no idea. So L equals 0 is S, F1, 2, 3. What is the name for 12? Who knows?
GI.
Yeah, so essentially that's the phase diagram. Well, it definitely says something else. It says, okay, even P wave ultimately goes below S wave for RS close to 1.2. But that's where you may say, okay, yeah, probably I don't trust perturbation theory at this point because RPA is a perturbation theory. So the phase diagram, I think the phase diagram is pretty reliable here because RS is less than 1. And we actually checked for some leading vertex corrections. They're not that important, but they may be important for bigger values of RS. So the question whether the real system is S-wave superconductive without phonons becomes not exactly answered by this phase diagram. But at the RPA level, it is. This is 2D. You go to 3D, same answer. Simply every value for RS which you see here will probably increase by a factor of 2 or 3. I think by S channel goes superconducting at RS equal 2 if I do a 3D. But similar phase diagram, simply all those numbers are increased by a factor of 2 or 3. And then you start trusting the whole picture even less. At the RPA level, definitely. Coulomb interactions for RS bigger than 2 will give you superconductivity in the S channel. By the physics which I just described. Yep.
So from this plot, what we are getting is for weaker Coulomb repulsions, the higher harmonics become more important.
Yeah.
But isn't it a little counterintuitive? As in, to get
intuitively, probably it's easy to say because Coulomb interaction and W function are strongly momentum dependent. When you do S wave, you just do global averaging on the Fermi surface and just hope for the rest. When you start playing with orbital channels, you have the choice kind of to pick up the channel which has the largest negative coupling. That's what Andrey was already kind of mentioning yesterday in the context of Kohn-Lattinger theory, Kohn-Lattinger mechanism. Saying, okay, well, just because if you screen interactions in real space, you immediately see Kohn-Fidel oscillations. In momentum space, it simply says, okay, the structure of the function in momentum space is such that if I multiply by the proper Legendre polynomial, the coefficient of expansion will go negative. You go to real space, and this is more or less picking up the eigenfunction, which just trying to pick up the biggest signal where your coupling is negative. So this is a Kohn-Lattinger explanation. And next slide will say this is not what's happening. It has nothing to do with Kohn-Lattinger. So all this phase diagram has no Kohn-Lattinger physics in it. So this is entirely because of dynamic screening. Simply dynamics of screening for different channels, that's how it works. And ultimately, yes, interactions are getting weaker, close to Fermi surface, and that's the answer.
Can I quick
Yeah.
question, just for clarification for everyone? You started with Conshan. And then you said that that story has nothing to do with reality and showed this picture.
No, Consham has everything with reality. I say, oh yeah, sorry. Bogolyubov, Tolmachov. No, just wait a second. Consham as the model is exactly solvable. It's correct answer. Whether real Coulomb interactions have anything to do with Consham model or Bogolyubov, Tolmachov, that's fake.
Okay, this is what everyone do.
Yeah.
The same way as I do. You show this picture.
Yeah.
In which, if you just say, I only want to focus on S wave.
Yes,
Nothing
only on this way.
Then you will get pretty much the same results as you were saying. The larger scatter, you have some fixed.
Wait. Bogolyubov, Tolmachov tell you that if I consider Coulomb interactions only, again, when I go to Bogolyubov, Tolmachov, I am talking about this phase diagram in the absence of electron phonon coupling.
Sure.
So this is Bogolyubov, Tolmachov in the absence of electron phonon coupling. Mu star equals gamma effective. There is no electron phonon coupling. Equals Coulomb interaction 1 plus GC rho F log bigger than 0 repulsive. TC equals 0 identically.
Sure. I must do clarification of something different.
Yeah.
If we forget for a second about electron phonon interaction,
Yeah.
just say we have a model
Yeah.
in which repulsive interaction is reduced at small frequencies.
Yes.
That's it. Is it the same story if, again, if I
Yeah,
forget
yeah,
about everything
absolutely,
else?
absolutely.
Yeah,
This
this
is
is what
the
I
same,
want
but
to
that's not Bogolyubov,
clarify.
Tolmachov, Anderson, Morel. Because Bogolyubov, Tolmachov, Anderson, Morel decided to ignore the frequency dependence, and they ended up with the positive number. Rachel Sham, Takada was before Rachel Sham, more or less the same couple of years. Those guys decided to include dynamic screening. And what they found? S-wave superconductivity without phonon. So literally, this result on the screen says the following. If Takada or Rachel Sham will compute mu star in the RPA model, which is much better, it's more reliable, they will get mu star less than 0 at RS bigger than 2 in 3D. So which means the first story is total fake. For all materials, RS is 2, 3, 4, and the story was developed to explain superconductivity in conventional materials. And they say mu star is bigger than 0. More realistic screening, and the calculation says, no, mu star is negative. Coulomb interactions are a pairing mechanism. It's not something which is hurting you. But then any material science, okay, yeah, I'm just going to this next slide, sorry. First, I just finished with Kohn-Lappinger. You can always check. You have, say, screening, dynamic screening. It gives you some phase diagram. But you also have 2 Fermi singularity in the polarization function, which gives you Confidel oscillations. And you can ask, okay, what those Confidel oscillations are precisely the reason why I have pairing in the high momentum states. For the Coulomb gas, the answer is no. So if I look at the Confidel oscillations and try to, and I can easily do it the following, you just use static W. It has Confidel oscillations. And you try to compute what will be the leading superconducting channel at different values of RS. That's this curve. But then you do dynamic RPA, and you see what is the leading superconducting channel now with dynamic screening. That's the green curve. And the answer is, well, when on the green curve, I try to understand what is the contribution of 2 Fermi singularity to my pairing. It's 1 part in a million. So for the Coulomb gas, 2 Fermi behavior has nothing to do with superconducting properties. You have much stronger attraction coming from dynamic behavior. 2 Fermi singularity is simply for Coulomb gas, it's subdominant at the level of 1 part in a million. So completely forget about 2 Fermi physics. Is contributing to the pairing. So if I do just static RPA, where is 2 Fermi, I would get the blue curve for different pairing channels. So I would pair here only at L equals 30 for this value of RS, while in fact I already have a pairing at a much smaller angular moment. Question?
Is there some variational Monte Carlo result that validates this in some regime? So is there some variational Monte Carlo?
There is nothing to validate here. It's an exact solution at the RPA level.
Yeah, but that
No, it's more. I'll coming to the ultimate solution. Just wait.
okay.
I'm just creating a story because okay, this is how it was developing more or less in the year. First, I already kind of told you the story. Now quickly, Electrons cannot pair, there is Coulomb repulsion. Let's ignore Coulomb interaction completely, do BCS. So we have BCS theory. Well, this still doesn't explain why electrons pair, because we have still Coulomb repulsion. Then this solution says, oh, that Coulomb repulsion will be suppressed, and that's why kind of electron-phonon interaction ultimately will win. 20 years later, roughly 20 years later, Takada, Rachel, and Shem say, just wait a second, no. Coulomb interactions for typical values of RS themselves are already glue. Which means the entire argument which was given to us before, that it's effectively repulsive, it's totally fake, the way how it was done. Actually, it was pretty universal, that's why it's so popular. You just write down this formula, assuming it's correct. You substitute Coulomb interaction, which is screened by the Thomas Fermi momentum. It happens to be the density of states times this number is exactly 1/2. Independent of RS, because charge has dropped, everything has dropped, density has dropped, nothing's left. For the parabolic dispersion relation, this combination is 1/2. You plug it into this expression when G rho F is 1/2, multiply this, of course, by the density of states, you get this. And assuming that the log between Fermi energy and Debye frequency is 100, you get a number which is 0.15. Right on spot to describe many, many superconductors. Slightly bigger log, and this can be, I don't know, 0.12 or 0.1. Everybody was extremely happy with this theory still happy, sorry. Almost all material science code are still happy with this picture. Yep.
This story is good, like 3D materials. There's something different in 2D materials.
Can you say louder, because I can't even repeat the question.
I'm saying that this is true for 3D material. There's something.
This is 3D homogeneous electron gas.
Yes. Yeah. I'm asking about 2D. Something.
2D, you saw the phase diagram for the 2D.
Behind his head.
The phase diagram was for 2D, and I'm saying the phase diagram is pretty similar for 3D as well. Simply everything shifts to larger values of RS. Yeah, there is no big difference between what I talk about 3D and 2D. Yeah, but what's the true story? Do we need a repulsive mu star or attractive mu star? Every material science code is saying, yeah, well, if I compute TC from electron-phonon coupling only, TC is too high. I have to make coupling weaker to make sure that I fix the experimentally observed TC. So mu star should be repulsive. But if I do RPA job, it's attractive. So which means all of this is fake, because I did a better job. So somehow we have to explain why people in material science using mu star close to 0.1 or 0.15, why all of this is working. And Andrey gave you answer yesterday. What was the answer? Probably Andrey cannot guess the answer. Make no mistakes. You know the answer, so which means make 2 mistakes, for example, and maybe they will count. Now that's how the story now is going. What else is missing? One piece is definitely missing. Remember my discussion that, well, when you have to sum up the product of 2 Green's functions in the interacting system, Green's function is renormalized. So the quasi-particle residue is not 1, and the effective mass is not unity, not the same as the bare mass. So the coefficient in front of log, apart from the density of states, which is the bare density of states, well, it will be renormalized by the effective mass. Sorry, it's the opposite ratio. It's m star divided by m. I'm sorry, in the wrong place. And times z squared. You say, okay, yeah, but maybe this is important. So that's the answer, which is now solved to very high level of accuracy for the homogeneous electron gas. So arrow bars assume they're shown. Well, this product, z squared m star divided by m0, that's what you have in addition to the log, which nobody in material science trying to account faithfully. Just ignore it. They just ignore. This product is completely ignored. Well, but you say, how can you ignore something which is already 0.5 at RS equals 3, but if I go to RS equals 4 and even further, that's probably 0.4. And you have to put it in the denominator of the exponent. You'll change your answer by a factor of 1,000 if you do it. and nobody is doing it. Well, what else is missing? With electron phonon coupling, we know there is a certain theorem, which I'll discuss a little bit, maybe Andrey will also discuss it, that if I take care of electron phonon interaction, I actually don't have to do vertex corrections because they are parametrically small, because Fermi energy is much smaller than the dBi frequency. We'll come to this question maybe several times. Much larger, sorry. Fermi energy is much larger than the dBi frequency. But for Coulomb interactions, none of this applies. For Coulomb interactions, vertex corrections are not small. That's exactly what is RS equal 1 is important. So if we just start asking, okay, what is effective coupling between fermions at low energies? It's not only bubbles. Just assume that every dashed line is screened. Well, I still have vertex corrections of this type, I have cross diagrams, and I have more mass. So I know some of the diagrams, but obviously the number of diagrams I can draw, say at order 6, it's already, I know, hundreds. All of those diagrams, they have no small parameters. So probably I have to include all of them to actually know what is mu star. Not just the bubbles or just screen Coulomb interaction, which is not good, but all of them. That's question number 1, because that's definitely a mistake. This is a huge mistake. This is probably also a big mistake. But there is yet another piece, which probably also requires consideration. When electrons couple to phonons, vertex corrections due to phonons are small, but vertex corrections due to Coulomb interactions have no small parameter. So even electron phonon coupling, dressed by further diagrams from the Coulomb interactions, are also important, and they're not perturbative. And they're also not doing it. In conventional Migdal-Agterberg theory, you drop this, probably factor of 2. You drop this, maybe factor of 2. You drop this, maybe factor of 2. Everywhere in the exponent. Hopefully I'm not confusing you, but that's kind of reality. And that's why kind of the whole history was so controversial that you basically start wondering, okay, what are we doing? From positive mu star to negative mu star. Take care of the Z factor. No, don't take care of the C factor. But of course, material science kind of practice is practice, which means they have to explain, they have to develop tools with some kind of reliable predictions for TC. And they developed this understanding that if I do Migdal-Agterberg theory, reduce the effective coupling by positive mu star, ignore effective mass, ignore the Z factor, don't do the vertex corrections. And this gives you a reasonable answer for a large number of superconductors. In this sense, it's not ab initio, it's just pure phenomenology of how some of the parameters have to be tuned to make realistic predictions, but it's not microscopic in any sense. Now for the homogeneous electron gas, I will try to say that we can finish the job. So let's see how it goes. Question number 1. If I take homogeneous electron gas, now this will be 3D. And I simply ask the question, okay, homogeneous electron gas, what is the effective mass renormalization? Again, I am trying to figure out properties of the electron gas when I have only one band. Again, much simpler than any material, spherical symmetry. So I can enjoy a lot of tools which are making my computation feasible. And that's why we can go to calculations which are very high order. Not me, actually, it's Kuhn, Hawley, and right now just other people as well. So they developed this technique. Sometimes it involves the statement variational diagrammatic Monte Carlo. It's conventional Feynman diagrams, but they with counter terms, formally making it exactly the same as the original model. But those counter terms allow you to maximize the efficiency how you converge to the right answer. And it can be done at the level of roughly diagrams up to order 6, everything included. So which means you are talking about thousands, probably Feynman diagrams at the end, and see what the answer is ultimately. So that's the solution. People had different predictions. So if I, for example, take this plot and say, okay, what the GW predicts for the effective mass? I'm somewhere probably on the first floor, given the graph, because you see it's from 1 to 0.94. But if for this value of RS, I just say, okay, what is the GW answer or RPE answer? It will be somewhere below the floor. Of course, people kind of are clever, so they just start manipulating and inventing a different type of approximation. They say, okay, don't do W, do W0. Why? No clue, but if we do it, let's say the blue curve. So the correct answer is kind of red curve. After the solution is done, now we have much better arrow bars, not sorry. we as a community. Now we have much better robots with effective mass. So this is the dashed line. Effective mass renormalization, which is completely ignored, is actually very small. So if I go to RS equal 4, we have less than 1% change for the effective mass of electrons. Strongly coupled electron gas. Everything is crumbled and tough. Effective mass for the electrons is just 1. Nothing happened.
The relation between this plot and another plot by Christian Howley that you showed before.
Oh, this is effective mass.
So
The other one was Z squared.
So everything goes into Z.
Everything is Z squared. Then you say, oh, okay, we have Z, which is large, but we also neglected vertex corrections for the electron phonon coupling. So let's do this. For every case when I have in the upper ladder, I have one Green's function, electron phonon vertex, and then there on the other hand, another Green's function with Z factor and electron phonon vertex. So the real interesting product which I have to consider is Z gamma 3. Well, also kind of a typical model or electron phonon interaction says electron is a charge. It couples to the ion, which is also a charge, maybe effective charge screened by the co-electrons, but still a charge. And then you simply say, okay, electron phonon coupling is given by the Coulomb interaction between the electrons and ions. And this is simply a displacement from the periodic potential created by the rigid lattice. So when ions vibrate, well, this is electron phonon coupling. This is displacement of atom from the equilibrium position Ra. Well, you see here that I have the derivative of the Coulomb interaction. So whatever comes from the derivative, it's extra factor of IQ. It goes to the coupling itself. Well, and you see that, well, in the Fourier form, this would be a Fourier component of the electron density times Coulomb interaction, and the rest I associate with electron phonon coupling. So that's the important combination. And that's the one which will be dressed from the Baer coupling, which is Coulomb coupling, electron phonon, which involves the result of the derivative, with including polarization, branches, and everything. And that's the diagram. But this one will be dressed by gamma 3. This will be dressed by Coulomb interactions, non-perturbatively. But again, remember in the Cooper ladder, it's always Z gamma 3. Each time I have a Green's function, I have gamma 3, another Green's function, another gamma 3. So you do now high order calculation for the product Z gamma 3 rho F WQ. W because, okay, this line will all be also screened because this is Baer Coulomb and I can always kind of insert a lot of bubbles in the middle. This is not perturbative. And again, W was already computed before up to order 6. So polarization of the homogeneous electron gas was done before. So it's already done up to 6-loop calculation. Now the calculation is extended to do also 6-loop calculation for Z gamma 3. And that's the total result. I don't know how you call it, but for RS equal 5, almost nothing. We are very close to unity. And second, in material science code, people develop kind of semi-phenomenological tool. Ignore Z, ignore gamma 3. Just do something which is called exchange correlation kernel, how to manipulate W. So that's what typically done in material science for this. It's a line. And we have the data for 6-loop calculation for the entire product. So it's reliable. Yes, they developed reliable phenomenological manipulation of how to use exchange correlation function in this place in order kind of to reproduce the entire behavior here. So whatever was done phenomenologically now, I would say just fully confirmed for the homogeneous electron gas. That's how you do it. Ignore Z, ignore gamma 3. But if you do everything, literally it says vertex corrections completely cancel properties of the Z factor. We know this is going to happen for Q equals 0. It's a zero momentum transfer on the Fermi surface. This is one of the theorems that self-energy normalizations and gamma 3 at zero momentum, they are related to each other. But whether this will work across the entire Fermi surface was not clear. Yeah.
If I may, when you refer to Q equal to 0, you obviously refer to word identity.
Yeah.
Word identity generally works for any Q on assuming that VFQ is much smaller than frequency. So what happens here? You have a vortex, but you probably calculate vortex at some frequency. Vortex on
No, this is of course vertex at zero frequency because the frequency is phonons and all the vertex corrections are coming from the electrons. Yes, it's zero frequency for sure.
So it's really
zero frequency. It's really zero frequency. Yeah. Yeah, that's why probably people who did it, they are clever enough, so they know diagrammatics. But again, just anybody calculating from first principles, because all of this is kind of good and nice for the homogeneous electron gas. But then you go to a lattice and you say, okay, well, in a real material, in a real lattice, now you have to worry about multi-band, clamp processes, and what then? But there is no technology to do it. So I'm simply saying, well, only if you do the entire technology without relying on any special theorems, you get the answer. But in material science, this is never done. And now kind of the final piece. So the fake story about Bogolyubov, Tolmachov, Anderson, Morel, because they did it through the log. Yep, sorry.
A previous slide. So it was unity only for RS is equal to 5.
Yeah, we did it only up to RS equal 5 because diagrammatics is getting more and more difficult when you go to bigger and bigger array.
So are we saying that most of the material science calculations are dealing with materials which have RS greater or close to 5, and that's why not including that term works?
Yeah. Now just let me go to the last piece. What is the effective electron-electron coupling at low energies? Why all the stories are more or less kind of cancel each other? We start with really fake story from Bogolyubov, Tolmachov that, okay, effective interactions are reduced because the moment you do a realistic screening, you immediately even change the sign. Yes, it's reduced, but to the level that you start changing the sign. But there are other diagrams. So if you do real diagrammatics, you say, yeah, of course, I have bubbles, I have other diagrams. And if I include all of them together, so that's the outcome. So you do order 1, 2, 3, 4, 5, 6. And that's how your effective low energy coupling, when you go to low and lower frequency. Again, Cooper ladders are accounted for completely, and you define Coulomb through the potential at a particular frequency. So the frequency is low, and I start lowering the temperature, and you see the answer. So if I go from order 1, order whatever 6, including all diagrams, the answer will saturate to something which is a 0.17. So this is for a particular value of RS. I forgot which one, this particular graph. So that's the story. It simply says that, yes, logarithms in the Cooper channel, they are important. But the moment I take care of the screening, they actually can overkill the Coulomb repulsion. But if I include other diagrams, they reinstate the Coulomb repulsion. And then for any value of RS, I think up to value of RS equal 5, this was done, we find that Coulomb interaction in the S channel is still effectively repulsive. So if you do the honest job, yes, that's the answer. Is it too fancy and complicated? It's up to you. So just, well, this is the whole story, how it was developing. And I would say just only high-order diagrammatics will ultimately tell you the answer. Again, all the answers I present for you are homogeneous electron gas. You say, how different from real materials? Probably completely different. For example, I told you that Kohn-Lattinger for Coulomb gas is just nothing. Maybe if I go on a lattice, and if it's not Coulomb interaction, but short-range interaction, like in helium-3, it's a totally different story. And maybe for short-range interactions or in material science and multiband, this is a very important mechanism. So I'm not responsible for that. I'm just simply saying you have to take care of this properly. Yeah, question.
Just to clarify, so what controls this diagrammatics at RS bigger
Sorry?
than 1? What controls your diagrammatics at RS bigger than 1?
Nothing. It can, okay, yeah. There is a paper by, the entire calculation was done outside of perturbation theory, definitely, because if it's RS equal 5, you say, do I have asymptotic series which will diverge? Definitely yes. How do you control it? So there is one paper by Stevenson, it's related to what Anderson, Feynman did before, it's called optimized perturbation theory. So let me explain what it is. I'll do it kind of in a slightly different example, but that's what was demonstrated by Stevenson. And Stevenson was saying, any mathematician will kill me right away, but it works. So that's the solution by Feynman, and Stevenson took it kind of further. Have a Hamiltonian. And suppose your Hamiltonian is H0, which is m omega 0 squared x squared divided by 2 plus kinetic energy plus H interaction, which is gx to power 4. Assume everything is kind of properly normalized. And I will say, okay, I would like to consider G much bigger than, say, omega 0, whatever is the proper parameters if I just normalize it to unity. Okay, make it 1 with proper normalization. So 1/2, and I have G much bigger than 1. I want to do perturbation theory for G. Everybody says, just wait, come on. Even for G much less than 1, this is asymptotic series. For a while, you are converging to something, but then you will blow. If G is a 41, you will blow right away. And how you blow? Well, okay, diagrams of order n will simply start diverging as roughly as double n minus 1 double factorial. Which means, okay, I probably have here G to power n, but good luck. So that's how your answer will look like. Suppose you compute energy. What's the correct answer? Okay, doesn't work. The solution, H equals H fake. H fake equals some number, we'll call it number C. C divided by 2 x squared plus H interaction plus H0 minus H fake. So that's your extra term. And I will make C whatever and start doing perturbation theory. You do lowest order perturbation theory, you have E1. Well, probably I know it has, maybe it has even lowest order perturbation theory correction, which we could, yeah, it's E1 because it's diagonal matrix element. You do lowest order perturbation theory, it depends on C. You have C here, you have C here. In both places. You say, okay, what's the big deal? I say, yeah, I'm trying to make H fake big enough, maybe it compensates something which is contributing from H interaction for this G. You do this one. Formally, you can see how it depends on C. It just does something. And you say, okay, I will look for the point where DEC over DC equals 0. Why? Well, I'm trying to solve this Hamiltonian. And my fake, I added and subtracted. So my answer ultimately should not be dependent on C. It's my arbitrary choice. I added and subtracted. And ultimately, with high order perturbation theory, I would like to get the answer, which is the physical one, which is C independent. Why not I don't start from the very beginning, do first order perturbation theory, and compute C from this condition. That's the C which I will use for the first order perturbation theory. Okay, so let's call it C1 because it was computed from this. Then you say, okay, let's do second order perturbation theory. I'll do exactly the same up to second order perturbation theory, but the curve will be different. It will be some other curve. Now this will be a second order perturbation theory is done. And this is my C2. And again, the result for the second order perturbation theory will be taken at the point where the answer is less sensitive to your arbitrary choice. Keep doing it. And that's the answer. So each time, it's not conventional perturbation theory. This is mathematical nonsense. Because I'm not doing Taylor series. Each time I solve next order perturbation theory, I'm working with a different Hamiltonian and different perturbation. And each time I kind of fine tune it to something else. So next order has nothing to do with the previous order. The calculation is kind of the same. Maybe I know some of the numbers are the same, but the whole expression is totally different. You do it, and that's the answer. E as a function of n, expansion order, for G of for the 1, and even for G larger than 1. Boom. And you get it, I know, with accuracy of 10 minus 10, relatively easy. You definitely start with something which is outside of any perturbation theory from the very beginning. You do one shot, you're already not bad. Even though you take quartic term much bigger than the quadratic one. Just read this paper, it's kind of beautiful paper, very easy to read. And the author immediately tells you that, okay, what I'm doing is mathematically not sounded, whatever. So maybe the other statement which was similar was given by Heaviside, who was introducing Maxwell equations. He was solving them. He's the one who introduced the step function, and every mathematician was freaking out. Those are discontinuous functions. You cannot write them. And he said, okay, but it's useful for solving equations. And it's the same as I'm not going to stop eating because I don't understand how my stomach works. Yeah. It's a paper by Stevenson. And it's called optimized perturbation theory.
What is the limitation of this theory? So when it will.
None is known. None is known. And you have a poster, which is variational diagrammatic Monte Carlo. This is done precisely using this technique. Maybe the reference to Stevenson is there, I'm not sure. But that's how it's called, yeah, and this.
Maybe putting you back to what you were telling us, maybe it's a question which I assume some of us may have. You showed us at some point, you showed us your own calculations, which showed S-wave superconductivity.
At the RPA level.
And you said that you include renormalization of the green function.
Yeah.
So Z factor was there.
Yeah.
Then, what I understand, you said that vertex corrections kill Z factor.
Yeah.
But in this respect, vertex corrections work in favor of superconductivity.
Yeah.
Because small Z factor.
Yeah.
And then,
But I was talking about superconductivity in the sense whether it's positive or negative. This was defined whether you're superconducting or not. How small is TC was less relevant.
Sure. But then the question is, what was wrong with calculations which gave TC or gave S-wave pairing? What eventually went wrong? Because at the end of the day, you said
what went wrong is that RS bigger than 1 or close to 1 in 3D.
Yes.
In 2D, probably we have to do the job again. So in 3D, what went wrong? You do RPA and you have S-wave superconductivity from Coulomb interaction.
Yes.
I say, okay, yeah, but RS equal 2 is probably already non-perturbative. Let's add additional diagrams. Let's add, for example, this diagram. And let's, on top of this one, add this diagram. And this diagram. And everything up to order 6. And do optimized perturbation theory. What's the result? Repulsion. And including bubble, sorry. And somewhere in the middle, of course, you have also bubble. But if I do just this, it's attraction. If I do static Coulomb screened by kappa squared in denominator, this is repulsion. But it's totally fake because the moment I screen, it becomes attractive. But the moment I do all the diagrams, it's repulsive again. I have to go beyond RPA to get the repulsion. Which means if I do RPA, it's completely unreliable and actually wrong sign if I go to large values of RS.
So it's not simply like vertex correction kills Z factor.
No. Vertex
like
correction kills Z factor. It simply makes the whole answer bigger. But the sign of the answer depends on this only. Yeah, okay, this is too fancy and complicated, but let me go to where we stand currently. So we have physics of scenarios. Sorry, Daniel. So you write down the Hamiltonian and you say, okay, let's do pairing in this symmetry channel. And you have wonderful answers and wonderful physics, maybe even explaining what you see in some materials. But the question is, okay, where this coupling is coming from? Why this particular coupling gives you the correct answer if you have Coulomb area interaction? And usually none job is done honestly. Yes, you can do perturbation theory, you have motivation, you have a scenario, but not the full solution for RS equal to 1, 2, 3, 4, 5. So, and that's the problem. The physics of scenarios works, and that's what most of us are interested in, and we develop wonderful stuff. Does it apply to any material? You ask a material science person. And the material science person said, okay, just sorry, guys. If you are talking about real materials, none of this exists. Because if there is no electron phonon coupling, there is no TC. Why? Because we are using phenomenological mu star, which is repulsive. You switch off electron phonon coupling, we have nothing left. And that's where we are currently. More or less, we are stuck. We're developing wonderful physics, explaining materials and everything else. But the moment you try to do whatever best job you can do for the real material using material science codes, with all the ingredients there, they cannot give you TC. Without electron phonon coupling, the answer will be 0. We are just at the beginning of changing this culture. And honestly, out of all people I talked to, Christian Howley is the only one who is more or less moving in the direction of changing this to something better. That you have to deal with Coulomb interactions better, maybe to higher order than standard DMFT, to produce something which probably will give you attraction from Coulomb interactions without phonon. So you can develop realistic predictions, what happens in a particular material, why do you pair in a particular channel, how to get attraction from Coulomb interactions in the first place. So far, all of this is extremely hard for material science, almost impossible. So that's why I would say, yeah, probably sounds fancy and complicated, but that's the dilemma which we face. There was a question which is now slightly controversial because I don't know the answer, the proper answer. I don't know the proper answer. I was arguing that, okay, looking for singular response is a very good tool to compute properties of superconductors, but maybe I have to be slightly more restrictive in a sense. This is a wonderful tool because I can employ perturbation theory, high order perturbation theory, decompose the answer and finish it. But it's good only if TC is much smaller than Fermi energy. I have well-defined Fermi surface. I'm not even saying this is Fermi liquid state. Andrey will discuss more or less within the same setup, roughly the same setup, even non-Fermi liquid states. But we do have a Fermi surface. And TC is much smaller than this Fermi energy. Under those conditions, I think we are doing a good job with this equation. It's a good tool to get the answer. But then several people asked me, and I didn't quite know the correct response to this. Can we have alpha maximum bigger than 1 and not a superconducting state? Strictly speaking, I need alpha equals 1 for superfluid response. I don't care whether alpha is less than 1 or alpha is bigger than 1. Maybe if all alphas, all eigenvalues are bigger than 1, I'm still not superconducting for a very simple reason. I never produce a singularity. So I'm still kind of in the normal state. But then something has to radically change. When I'm talking about infinite size matrices, I was looking for the largest eigenvalue. To do something else, I have to completely reconstruct the spectrum of my equation so that all eigenvalues now are bigger than 1, and even the smallest one is not touching. So this is kind of radical reconsideration of what happens in the system. Is it possible or not? I'm still kind of slightly confused. So under conditions which you see on the screen, probably it's okay to look for the maximum eigenvalue. Maybe under different conditions, you have to look for the minimum eigenvalue, which will reach 1. And let me specify, okay, under what conditions maybe potentially this is happening, because I will do the following. Suppose I fix temperature, 0.2 Fermi energy. Everything is fine. And I'll start increasing the attractive interaction. Increase. I don't need any log anymore. You say, okay, yeah, we had 1 because we have effective interaction, density of states log. If interaction is weak, I need large log. But if interaction is large, I don't need a log anymore. Maybe my V rho F is already 1 all by itself. And then in addition, you start remembering what Andrey was saying. Well, apart from kind of what we call Cooper ladder, once we go to energies above Fermi energy, let me kind of same Cooper channel, but I will call it, I know, particle scattering in vacuum. Well, which means I don't even care about the Fermi surface. If 2 particles go to energies much bigger than Fermi energy, they will propagate and interact as if other particles don't even exist. This is how you kind of deal with the logarithmic divergence in your integrals. When you go to energies much bigger than Fermi energy, you say, yeah, but this is simply responsible that I have to go from potential to the scattering length. Because 2 particles in vacuum, they just enter, they exit, and this is characterized by scattering length, not by the original potential. Okay, remember this discussion? It's not Cooper log formally, because this is not related to behavior close to the Fermi surface. It's just something which is happening potentially non-perturbatively at high energies. But this can create a bound state. So which means my gamma will go through a pole in frequency because you will start, and this frequency can be, I know, small, because if it's shallow bound state or comparable to Fermi energy, so it's a relevant pole which you create in gamma because you create a bound state between 2 particles in vacuum. Maybe this is what actually leads to very strong spectrum reconstruction, because what emerges on the other side, keep increasing V. The bound state energy will become bigger than Fermi energy. And then the description of the Fermi system becomes totally fake, because now the right degrees of freedom are pairs, they are bosonic particles. Those bosons interact. They interact because if they come close to each other, they can even exchange fermions places. There is Pauli repulsion principle if they are compact enough. So ultimately, even if you have strong attractive interactions, the effective interaction between bosons is repulsive. For the unitary Fermi gas, this was computed. So that's the total reconsideration of the picture when there is no Fermi surface, The right degrees of freedom are not even fermions. The product of two Green's functions, which I have here, is better replaced with bosonic propagator because they propagate like a pair, which is totally very closely linked to each other by high energy physics. So the bosonic description is much better. My belief is that this equation is still okay to predict the single response. Whether this is through the largest eigenvalue or, as I was discussing with Alex, there is kind of very peculiar system like Josephson droplets with very weak Josephson links. The question is, okay, what this equation will predict for this system? Obviously, if I have large droplets, there will be something which, like TC, when the droplet would go superfluid if it was in the bulk. Definitely at this point, some of the alpha T is getting close to 1. Because if the droplet is very large, obviously I have almost a singular response, which means one eigenvalue is definitely getting close to 1, and the physics is just like in a Fermi liquid. But then you just discovered, okay, well, the droplet is disconnected, charging energy is bigger than Josephson coupling, and globally the system of Josephson links is not superconducting, it's normal. How to describe this using this equation? I would say probably it's possible, but it's horrible, and I just don't actually know. But the better description of the same model is called a quantum rotor model, or bosonic system with large occupation numbers, which is completely and easily can be solved by other means. We know how to do it on a different perspective from the bosonic language, or phase density relations and everything else related to it. So let's say that, well, this equation is a good computational tool for existing Fermi surface at temperatures much smaller than Fermi energy. The moment you totally reconstruct the effective degrees of freedom in your system and you create, say, bosons because of the strong coupling, I'm not saying this is probably a good tool. Switch to bosons. And I will switch to bosons in my last lecture. This will precisely bipolar on superconductivity when attraction is strong enough to form pairs. And probably I will just stop at this, just say, okay, how difficult it is to solve the problem once electrons form bosons. Very easy. That's the answer. You can say, yeah, but the bosons are interacting. You say, I don't care. TC will not change. So which means the other limit turns out to be extremely easy no matter what are the strong correlations. The moment you form bosons, you know TC. Just don't even bother computing. As long as bosons don't phase separate, they create a solid, that's the answer. Yeah, I'll stop.
For questions.
Something I probably will ask first.
Where there, Andrey?
That's the question.
So for this optimized perturbation theory that we talked about.
Yeah.
I don't see why with the parameter C it must be extremized. Like why couldn't it just be strictly monotonic function? Like why did it happen?
Why it has to go to further up?
Yeah, like why is the condition that there's some point where the derivative is 0?
Oh,
Like why is it generically true?
well, you see this Hamiltonian, this Hamiltonian. This is C independent. It has nothing to do with C.
Sure.
It has G. This is also C independent.
Good.
But I'm not solving it faithfully, which means I am having an approximation for the answer, but I know that I need an answer which does not depend on my arbitrary choice. So what would be the best guess for the correct answer, given that the final answer should not depend on C, if I have an answer which depends on C? You go to a point where it's least sensitive to C. So I go to the place where the derivative is 0. That's it. There is no other mathematical justification for anything.
Just using these energies, I don't see like. So like there's many functions that you could find where it would have no external.
Typically, that's what you have to try. Well, this example is kind of figured out in the paper, so you just do it. Yes, you have energy as a function of C. It has a maximum. Take it.
And you said there's no.
You do second order perturbation theory. You have a maximum. Take it.
You generically find that.
What you also generically find, if I just plot, this is E2. So this is say E10. The curve is getting very, 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 very flat as a function of C. So which means, okay, just you are getting less and less important where you actually take the point. Yeah, you still have a maximum, but the curve is creating very, very flat behavior.
And here, the word which is confusing is perturbation, because it's.
Perturbation, I just do perturbation theory, and how many times I use this standard perturbation theory. Do it this way. Put here psi, and this is number of psi's included in the answer. Ultimately, psi you put to 1. When you analyze this curve, you do it for psi equal 1, but the power counting is in terms of in the powers of psi. How many times in the perturbation theory I was using psi?
We're taking each thing as the exact one and then
Yeah, well, this is just for counting. I'm just saying, I assume that this is a perturbation, and I do lowest order perturbation theory, second order perturbation theory, third order perturbation theory in this term. Yeah. There was a question there, so yeah, just because we agreed.
How the calculation is different from the Kohn-Luttinger because alpha is also your eigenvalue.
Sorry, can you say louder?
So how the calculation is different from Kohn-Luttinger mechanism what Andrey was talking yesterday?
How it's different when I do diagram?
Yeah. Kohn-Luttinger. How it's different from Kohn-Luttinger?
Kohn-Luttinger is more or less, say, second order calculation. You include some diagrams of, say, higher than the first order. You include bubbles, for example, and you also include vertex corrections. So that's what Kohn-Luttinger did for the short range interaction.
Well, I'm just going to say that I will be talking in length.
Yeah, Andrey will discuss it, but okay. Kohn-Luttinger is simply just going beyond the lowest order perturbation theory for your coupling. So you say, okay, I have helium, purely repulsive. It's original potential. It's frequency independent. It's function of R. But then you say, yeah, what high order diagrams will give you? They will give you dynamic screening. They didn't care about this. They write down the statically screened potential, but you also have vertex corrections. And you can calculate what comes from the 2 Fermi singularity in those diagrams. And they discovered that, well, okay, if I write down coupling at high order in the perturbation theory, not the lowest, but at least second and further, and I look at the Fermi singularity, and I try to analyze its structure in momentum space, then they figured out at what orbital channel you actually get a negative expansion coefficient, which gives you attraction in this channel. And they were arguing this way that, okay, in any system with short range interactions, in any system, Fermi liquid state is unstable. Because sooner or later you will find an orbital channel where you have attraction, and ultimately, because channels are decoupled, the system will go superfluid in this channel. Yeah, sorry. Yeah, I should not do it because Andrey will.
Maybe I will ask one question, not on the practical importance, but as a matter of principle. You put a statement, which is very bold statement, that without electron phonon interactions, there is nothing and TC is.
No, it's material science code.
Material science. Okay, fine. But you showed your slide in which you said S wave, P wave, G wave, I wave, etc. And the line continues.
Yeah.
To smaller and smaller RS.
Yeah.
Let me take a Gedanken experiment and take a limit when RS goes to 0.
Yep.
Then vertex corrections are irrelevant, Z factor is irrelevant, M star over M is irrelevant, but you still get something.
Yeah.
Why this is wrong?
No, this is correct.
Then how it's related to the questions that there is nothing.
In the S channel, there is nothing in the S channel.
Well, S channel or general.
No, S channel only.
But then the question is why we need electron phonon for a situation we know from experiment that is not.
No, if it's not S wave, you are in a much better position. Sure.
Okay, then I misunderstood.
You are in a much better. No, I was talking about
the
whole controversy was, which I was trying to develop, was electron phonon coupling is for S wave superconductors, more or less generic. And then suddenly Coulomb interactions as if it's something hurting you because they are repulsive. And the whole story was from repulsive to attractive, this or that. The ultimate story answer is yes, they are repulsive, but not for reasons which people put before. When it goes to high orbital channels, so this phase diagram says you go to smaller and smaller values of RS. That's the dominant orbital channel for smaller values of RS. So it's RS 0.1, okay, the curve stops. For RS somewhere here, the leading orbital channel, I don't remember, maybe 15. And it will continue, of course. But because RS is small, you don't care about anything else. So that's RPA is probably at the end of the job.
This is what I was.
Yeah, the RPA is already done and you don't have to.
Yeah.
Yeah, you cannot avoid doing RPA because otherwise your diagrams are divergent. So you have to do screening, but after that, you're done. Yeah. For high orbital channels, yeah, Coulomb interactions are doing much better job. P wave probably will be the most important thing. If I kill S, I'll say high order diagrams will kill S. So then the possibility is open for P wave. It's much easier. But again, if you want P wave at larger values of RS, the job was not done yet. What is the effective coupling in the P wave? We didn't do the job yet.
Yeah. So is the frequency dependence of the gap function measurable?
Frequency dependence of the gap function is always important if you discuss a S wave, because you definitely have repulsion at high frequencies. If you develop something else at low frequencies, you have to change the sign.
I mean, if it is measurable.
I think it's measurable in tunneling experiments. So that's how it was done for conventional superconductors. People were deducing properties of the gap function from the properties of the spectra, in tunneling spectra. Again, I'm not too much in the business of the gap function because I'm talking about how to get TC or what's the right mechanism, what's the right picture. But yes, the gap functions, they actually have pretty strange behavior in the real in the momentum space as well. Usually this is not discussed, but this is not also a non-trivial structure. And your homework actually will force you to think why combining two mechanisms, both superconducting, makes life more difficult, make much worse. You have one glue, another glue, you take them together, and it's much worse. And this goes precisely to the structure of the gap function and momentum space.
Do you know what disorder would do with this picture? I mean,
No idea. No, I know what it will do for S wave if it's weak.
Yeah.
But you also know.
Right. Is there an analog of Anderson theorem for your mechanism?
For S wave, if it's weak, there is. For P wave, probably there is none, according to everything we know. So static disorder, conventional disorder. Yeah, probably will start killing orbital channels higher than S. And there is Anderson considerations that a weak disorder for S wave will not hurt it. But unfortunately, it's not the complete picture because, okay, you of course know there is a community of people originating from, say, Trieste or around. They say that if you make very strong disorder in S wave superconductor, ultimately it can create a peak in TC close to the edge of Anderson localization. I believe this is solvable. Nobody took the job to solve it. Because what you have to do for this, you have a directive U Hubbard model with small u. There are exact methods to do it. You add very strong disorder, but you can easily diagonalize a system of 100 by 100. 10,000 metrics can be diagonalized exactly. So you tabulate the Green's function in the presence of strong disorder when you are formally almost localized everywhere on the sides of the sample. But it's attractive U Hubbard model. So which means you can track how TC behaves on the edge of Anderson localization on the sample size. If it's two-dimensional, of course, every single particle state is localized, but there is localization length. So you can always take disorder in such a way that localization length, say, in the middle of the band is bigger or smaller than the size, and simply check how TC behaves. Nobody did the calculation. The argument does not depend on dimension. People just say if you have very, very strong disorder, it may increase TC. For Coulomb interactions, there is another school, I know, Finkelstein and others. They say, okay, if it's Coulomb interactions, you will suppress TC by disorder. If it's strong disorder, Coulomb interaction, and the Coulomb interactions in the system, you will suppress TC. But I'm talking about, say, I know, negative U contact interaction and strong disorder. Then some people predict that TC will go through a maximum close to the edge of Anderson localization. Yeah, that's what I know. But again, nothing was solved reliably, so I have no clue what the right answer is. But at least those are the predictions. Yeah.
I can pick it up.
No. No, because he is out of the blue. It's nothing to do with the original plan. I didn't intend to, it has no school. I just out of the blue, I say, okay, I'll throw.
Because the nerve doesn't care that it has to be shipped.
This is 6 months. No, this is 12.
That's what we have to add this at the end. Plus one product. That's 3 days. You can release the conversation. You're like, yeah, I'll be working. Then you want to her. I didn't want to get wrong. But not both. Yeah, I ordered it.
Oh, sorry.
No.
Okay, so. What? Yeah, okay, good. So then it's some time to. Okay, let's go. Okay, so let me continue with what I'm doing. And it will be in fact pretty similar to what Nikolay was saying and partly to what Daniel was saying today. So the word Konlatinger has already been pronounced. So let's see what the story is about. And as happens in many other theories, like Agterberg theory, it can be theory, it can be computational procedure. So nowadays, what's called Konlatinger is treated as computational procedure, but it started as a well-established and well-justified theory. So let me go in steps. So let me remind you where we are. We said last time that if I take interaction, generally u of k minus p, and I take both k on the formula, I think I use pf, and p is also pf, so I put both formulas on the Fermi surface, then this interaction can be expanded in harmonics, such that in 3 dimensions, this is sum over L to L plus 1 UL PL of cosine theta, where theta is obviously the angle between K and P, both on the Fermi surface. And then we had wonderful story with pairing channel, particle-particle channel, that once we then sum up all these ladder diagrams, which are chosen because they are logarithmically singular, then the dressed interaction, let's call it U bar, which is also a function K minus P. Graphically, this is our original interaction, and this is dressed interaction. And of course, we keep in mind that we need to anti-symmetrize it, and we discussed it last time. So this interaction can also be expanded in harmonics to L plus 1 U bar L PL of cosine theta. And nice thing is that UL bar is only expressed in terms of UL, 1 plus UL, MPF over 2 pi square, and then logarithm upper cutoff divided by, say, frequency. Again, without looking at whether it should be I pi over 2, just keep logarithmical occurrence. Great, this is what we had last time. And again, beauty here is that there is no integral relation. I mean, fully dressed interaction with angular momentum L is expressed only in terms of the interaction with momentum L. And this raised the possibility, Anderson-Morel papers was already mentioned by Nikolay. There was another paper by Landau-Pitayevsky about the same, that it may be that it's enough to have that somehow repulsive interaction, when you look at it through a magnifying glass, will eventually have at least one component which is attractive. And if just one component is attractive, then you immediately see instability. It's enough to have negative UL here in order to get singularity of this denominator, because omega-like temperature is in my hands. It's a parameter that I can vary and make as small as possible, right? Okay, and this brought us to the issue about Kohn-Luttinger, which the story started with the observation, which I already put on a whiteboard at the end of previous lecture, that if you look at statically screened Coulomb interaction, then U of R as a function of coordinate, interaction initially dies off as 1 over R e to minus R over xi, but at large distances it has oscillations in the form cosine 2k of R over R cubed in 3 dimensions. And these oscillations obviously raise the question that there is occasional overscreening. Interaction changes sign. And so big question was, is it enough to have one component of the interaction which will be attractive? Or under screenings which you see here will win all the time? And this is a question which in fact was addressed by Kohn and Luttinger. And the idea is this. So before I go, first let me say this. In connection with the previous lecture, I assume from the beginning, and then we'll try to, actually I cannot really justify it, but I will just try to make some arguments, that like Nikolay said, if you include all diagrams, not only just standard bubble renormalization or RPA renormalization of the interaction, then your effective interaction as a function of frequency, let's call this interaction in terms of now momentum and frequency. So I'm mostly interested in frequency dependence of the interaction. Remember, if you do RPA at a fixed Q, remember, if you do RPA, then you get something that goes like this. Interaction increases as a function of frequency. And that was the source of the discussion about possible superconductivity from Coulomb interaction. I will assume that if you include all diagrams, like Nikolay said, you will get, instead of this one, you will get behavior when interaction will die off as a function of frequency. I don't think there is any way to really prove this, but I will just assume that this holds. And this means that I don't need to worry about high frequency parts. The interaction will be just dying function of frequency. And then I'll focus what happens here. At small frequencies, and obviously I will be interested in situation when TC is pretty small, which means the typical frequency which you need here are small for one reason or another. And therefore, I will look at static interaction. So this is the reasoning to look into static interaction. Very good. Now, again, referring to yesterday lecture by Nikolay, he said that when you look at pairing, you need to be careful in how you define quantum. And we used to say, well, this is our full interaction, which will be bare one plus we renormalize it in a particle-particle channel, do it again and again and again, and every time we get log omega naught divided by omega, and this is how, summing up all these terms, we obtain series of Cooper logarithms. But the correct statement is somewhat different.
The correct statement, really correct statement from the point of view of theory is this. You first of all need to define what is called irreducible, sorry, what is called, right, irreducible interaction in a particle-particle channel. What I mean, besides this ladder, there is infinite series of other graphs. And for example, standard ladder, standard bubble renormalization like this is part of what you have besides particle-particle, right? So let me do this. Let me first of all collect all graphs which cannot be cut like I did here by two fermions with momenta k and minus k and with frequencies omega and minus omega. Well, let's be careful, I put it omega, so let me do it like this. It's approximately k and minus k, and of course, approximately omega and minus omega if I allow something to come in here. So I select all diagrams which I cannot cut by two fermionic lines with arrows pointing in the same direction, which means, in other words, everything but pairing channel. And I'll call all these diagrams, which are examples, as I said, like this one, like that one, etc., etc. Let me call this by totally irreducible interaction in a particle-particle channel. Let me label them as, I'll put it like this, in order to distinguish from the full one. And then obviously the series for the full interaction, we'll go through this mathematics very quickly. Series for the full interaction will be like this. It will be everything but particle-particle channel plus this and this again, plus do it 3 times. Sorry. Etc. You saw this yesterday in Nikolay's lecture. The goal is now to say this, that if I replace this by Bayer interaction, this will be my repulsion. I will not get anything. By Bayer interaction, I mean either Coulomb interaction or Hubbard interaction, the regular screen Coulomb. I will not include these terms. Where these terms come from? From screening, right? So I need to include screening. And of course, I need to include all diagrams that give screening, not necessarily RPA diagram. So my goal will be to calculate this quantity and include into this quantity this physical effect that interaction occasionally become over screen, and then see what I get. And in order to do this, we need to understand, first of all, where this Friedel oscillation come from. And they come from the fact that if I look into renormalization coming from particle-hole bubbles, then this polarization, particle-hole polarization has a singularity at 2K. So let me first of all write down just first few diagrams, and then you will see what I'm talking about. So I want to calculate this quantity. And again, we'll do calculations accurately. But first of all, let's write down first few diagrams. Just do perturbation theory. It's equal to Bayer 1 plus screening like this, plus I can do this that term. I can inverse. I can do this. This is wavy line. And also, let's put it from here. I can write exchange. Right? And don't forget that we'll need to antisymmetrize. So I will take this guy, I will need to antisymmetrize, right? But at this stage, antisymmetrization will come as a necessary step in our calculation. Right now, I want to tell you one thing, something that I'm sure you know, that if you calculate internal part here, or you calculate internal part here, or here, or here. Because you see, despite that it looks that two arrows are pointing in the same direction, this is not particle-Hall channel. So this is not particle-particle channel. This is particle-Hall channel. How we know this? In the particle-particle channel, if one momentum is k, another will be minus k, right? Let's see what momenta are here. Let's do this diagram more accurately. I'll just counting momenta. K and minus k are incoming. P and minus P are outgoing. Let me call this momentum L1. Let me call this momentum L2. And then let's count momentum conservation. So, for example, I'll take this vertex. Incoming are L1 and minus K. And outgoing are P and L2. P plus L2. I hope you see it, right? For this vertex, incoming are L1 and minus K, outgoing are P and L2, which means that L1 minus L2 will be equal to P plus K. And this is a condition for particle-Hall, right? We fix difference between momenta, not sum of the momenta, right? So each of these graphs will contain what is called particle-Hall polarization bubble, which can be either a function of k minus p, like here. If this is k, this is p. And then, of course, the difference, if I put L1 and L2 here, then the difference between the two momenta, momentum conservation here, will be L1 plus k is equal to L2 plus p, or L1 minus L2 will be equal to p minus k. Let's put momenta everywhere here. But again, L1 minus L2, L1 minus L2 here. All of them are particle-Hall bubble. We can generally calculate particle-Hall polarization with as a function of generic momentum q. I guess this is what is known as Lincoln function. So something that I'm sure you did one way or another in calculations. And you can write down pi. Let's call this quantity pi. Pi here of k minus p or p minus k doesn't matter, because of course function will be symmetric with it. It will depend on the modulus of the difference. And this is equally will be p of k plus p. And I put subindex pH means particle-Hall, just to distinguish it from particle-particle. So if I plot PA particle-Hall as a function of Q, and plot it graphically as a function of momentum, again, this is a function of modulus of Q because of rotational invariance. It cannot depend on any direction, right? It's rotational invariances. Then generally, as a function of Q, the function will look like this. And it will say, so what? Not a big deal. Some function, some decreasing function of momentum. But if you look carefully around the point Q equal to 2kF, you will find that there is something interesting here. Function is non-analytic. And non-analyticity of this function would mean, where I have this expression, yes, that close to 2kF or 2pF, I keep it, let's call it, let's always call Fermi momentum pF, not kF. So close to pF, the function has the form q minus 2pF divided by 2pF, which by itself would be trivial, just linear function, but times seemingly innocent dependence on the logarithm. 2pF divided by modulus q minus 2pF. Very good. The whole expression is also known analytically, but it's not that important for us at this moment. In fact, some of you may know that this singularity is exactly the one that gives us Friedel oscillations. So if you just do simple RPA calculations and add series of bubbles
and then write down your interaction u renormalized of q equal to u of q, 1 minus u of q times particle Hall polarization as a function of q, and then take Fourier transform to get back to dependence on coordinate. You will find that because this guy has this 2pf singularity, you get cosine 2pfr divided by r cubed oscillations of the Fourier transform. So this singularity is exactly the one that gives rise to Friedel oscillation. Very good. Now, by itself, we may say, so what? Here is so what. Let me now see what it gives for our purposes. Let me take, we'll do simple mathematics, which in fact you will do later. It will be part of your homework. Let me take any analytic function. Any function which has all derivatives of this function will be completely regular. So I get some function u of q, or u of theta, let's put it this way. Again, it's a function between two particles with momentum on the Fermi surface. Theta is the angle of k and p, right? So I take some arbitrary interaction as the function of theta. And take Fourier, transformation into Legendre component. So I want to see what's the form of UL. Remember, this is sum over L from 0 to infinity to L plus 1, UL, PL of cosine theta, this expansion and eigenfunction of momentum. Let's play the game. Who knows how U of L behave at large L?
1 over L plus A.
Sorry?
I don't remember.
Who knows the result? How it
1 over L
behaves?
to power 4.
Sorry?
1 over L to power 4.
No. This is a regular function.
Oh,
Function of whose
not the one which you have here?
No, not this one.
Oh, I see.
No. Regular function. Function which has all derivatives are completely regular. It's great that you don't know, because then you will have to figure it out. And this behaves as e to minus L. So regular function has exponentially decaying component of eigenfunctions of angular momentum. Now let me take this function. I just take the function as is. Okay? Yes. Let me call this function p tilde, particle Hall of Q. So with the risk that I change between u and p, I just want to take this function alone. And this is still function of q, right? And q is what? It's a momentum between two fermions on the Fermi surface, right? So what we really need to say, what is q? Remember, q, let's put it here, is either k minus p or k plus p. Let me put k minus p. So mod q will be equal to what? Square root of k square plus p square minus 2kp cosine theta. And when I say k square, let's say mod k square, mod p square, mod k, mod p, and theta is the angle between two, right? Vector a minus vector b squared. Good, which is equal to square root 2pf square 1 minus cosine theta, which translates into 2pf sine theta over 2. And I put sine theta over 2 because I don't need to consider any angle between, I can consider angle between between 0 and pi. It's enough, right? So sine is always positive. Very good. Mod q must be positive. Right? 1 minus cosine theta is 2 sine square theta, so this is the right expression. So this is a function of theta, right? Where I should stop? I should stop here, right?
This is where I'm interested in this function. I'm not interested in this function when Q is very large. This function doesn't describe function of the Fermi surface. So I need to consider only half of this singular piece, only the one that is here, before we reach 2P. Nevertheless, we can still do calculations, right? So I take this function, P tilde, which I write down as a function of theta, and translate it into P tilde L. And here I already had that. You probably cannot see this color, right? So I better use different colors. Okay, so write down P particle whole tilde of theta goes into P tilde L. And then I ask a question, and how this function behaves as a function of M. This function now non-analytic. Why non-analytic? Take, there's a logarithmical function here. It's a function x log x, right? Differentiate the function once, you get log x, the leading term. So function, the derivative diverges. Take second derivative, do even more divergent, etc., etc. So this is a function which has divergent derivative, non-analytic function. And I already had the answer. This goes as 1 over L to fourth power in 3 dimensions. And then story goes, and now I'm telling you Conn-Leitinger story. Story goes that then I don't care about this. Whatever it is, it will be exponentially small function. This function will also be small, but power law small. So this one definitely will win over any regular interaction, which means that when I write down graphs, I can forget about original interaction. I don't need to know what it is. But this was only part of the argument. Another part of the argument was that this singularity is actually, it looks like very simple, right? X log x singularity. But in fact, it's a part of interesting physics. And the physics generally was recognized many years later. And it was recognized as a hidden one-dimensionality in multidimensional systems. Namely, that this singularity reflects the fact that in multidimensional systems, there are special processes which involve only fermions going along one direction and coming back, but never scattering at any angle. I will tell you what it means. What it means specifically is this, that I want to write down what is the full result when I calculate this contribution. I take only this contribution from all diagrams, which is seemingly second order diagrams at this stage, but I want to see what coefficient is in front of this term. Namely, I go back, I write down again all 4 diagrams plus this one plus other way around. These are nicely called wine glass diagrams. Plus this one. And I want to see from each polarization, this one, this one, this one, I take only this term. And I want to see what the prefactor is. And I will do it this way. I will say, I don't know what this line is. This may be Yukawa screen-Coulomb interaction, or Yukawa screen-Coulomb interaction plus all terms that will not produce any non-analyticity. So I will assume that this is some interaction. Let's call it U tilde as a function of theta, of the angle. Remember, K and P, and there's the angle theta between the K and P here. This was important because this is what allows you to go beyond second order. And this is what Conn-Leitinger actually did. They said, we don't care what this interaction is. If this interaction is something regular, then I don't need to know what details of this interaction are, because all Legendre component of this interaction will be exponentially small. But what I want to do is to take arbitrary interaction and
calculate the prefactor, I'm repeating myself, calculate the prefactor of this term. And let me tell you what the result is. Now I will try to write the result Ekov. Because again, I keep saying in words, but we never put it on a whiteboard, that we need anti-symmetrized interaction, right? So as we discussed last time, there will be component which is spin triplet and component which are spin singlet, right? Here is the result. Let me erase this part, and I want to write down what the result will be. And the result will be that U bar will be equal to, it will be some function A of theta times singlet combination. Let's call it alpha, beta, gamma, delta. This is what we have all the time. So it will be I sigma y alpha gamma I sigma y beta delta. And I hope you realize that this is nothing but singlet combination. So this singlet channel. And here there is another term, of course, B of theta, triplet channel, sigma x alpha gamma, sigma x beta delta. That's not a big deal. We know that every interaction as a function of momentum transfer can be written as sum of singlet and triplet combination, right? Symmetric and anti-symmetric combination. What is interesting is this coefficient. And look how these coefficients look like. A of theta will be equal to, I only include this term. It will be minus twice u square, we call it u tilde square of pi, minus twice u tilde of 0, u tilde of pi, minus u tilde square of 0, times pi tilde, too many tilde, right? Particle whole of theta, plus pi tilde particle whole of pi minus theta over 2. This is one coefficient, A of theta. Let me write the second one and then we discuss. The coefficient B of theta will be equal to, again, minus twice u square of pi, u tilde square of pi, minus twice u tilde of 0, u tilde of pi, plus u tilde square of 0 times pi tilde particle whole of theta minus pi tilde particle whole pi minus theta. And you want to know how this guy looks like when I rewrite it in terms of theta. Not big deal. We can do it. Pi tilde of theta, particle whole tilde. When I do calculations, I say, of course, you remember there's a coefficient here, which I didn't write, right? So let me write it with the coefficient. It will be minus MPF divided by 16 pi square, and then 1 plus cosine theta times logarithm 1 plus cosine theta. You can immediately see when Q is equal to 2pf, theta is equal to pi, right? So this guy goes to 0, but it goes to 0 as x log x. That's exactly what you have here, x log x. Right? Very good. Now what is interesting in this formula? This exact formula. The most interesting part about this formula, seriously, is that prefactors contain only interaction at 0 momentum transfer, all interaction with 2kf momentum transfer. What is 0 momentum transfer? I go from k to essentially k. I go forward, right? What is 2pf momentum transfer or angle equal to pi? I go backwards, right? So it contains forward and back scattering. Notice this. There is no integral of theta, of u of theta, etc. Right? This is wonderful, right? Which means that only forward or only back scattering, nothing else. Very good. Now let's see what we have. Of course, I only wrote this term, right? There is, of course, also Bayer interaction. The one again, what is Bayer? We include all the normalization up to infinite order. But those, just 1 second, those who will not produce, which will not produce us singular contribution. So everything except for this is included to infinite order, assuming that there is nothing else, right? Assuming that this is the only singular piece that we have. Yes.
So this expression A and B, is that like an approximation where you only consider the theta dependence in pi but not in u tilde?
No. Theta is theta. It's either close to 0 or close to pi. But the coefficients are computed exactly. The coefficients are exactly u of pi or u of 0.
I mean, this happens near 2pa, right?
This happens near theta. The theta is here, and you see this is a number. This is just a number, coefficient.
How do you get pi and 0 there exactly?
How you get pi and 0 there?
Yeah, I mean,
You actually see it because you may find out what is this. What you really need to do is this. This is K, this is P, right? This is L1, this is L2, right? You need to integrate over intermediate L, right? It turns out that only tiny fraction of L contributes to this result. Which one? Such that basically everywhere here, this will be interaction as a function of K minus P, right? This K minus P will be close to 0. Sorry, will be close to 2kf. This means that you will get here interaction close to 2kf, right? This is what gives you u of pi. In this diagram, you can check that you get interaction at 0 momentum transfer.
it's like k minus k go to minus kk or k minus x.
Yeah. Okay, yes. Yeah.
When you are writing all
No, just louder a little bit.
when you are writing all the irreducible diagrams,
Uh-huh.
you also had the Bayer term there.
Yes.
But when we are writing the renormalized interaction, we only have the particle whole as a function of Q. Is there a reason why we are ignoring?
Yes, let me say it again. The reason I write only term of second order is that I already know that at large angular momentum, Bayer term will scale as e to minus L. Right? Very good. We'll figure out in a second what will happen with this term, but we'll do it in a second. Again, I want to emphasize again one thing. This is not Bayer interaction. This is Bayer interaction plus all the normalization which are regular. We just call it some unknown function. Yes.
Yeah, did you assume half unit here because you?
Did I assume what?
Did you assume the half unit?
No, absolutely not.
Okay, but you take this pi equals to kf, right?
No. I had momentum transfer. It has nothing to do with half finite.
Okay.
I have Fermi surface. This is, let's take simple quadratic dispersion. I have my chemical potential is something here, which is pf square over 2m. If it's, I don't have to take quadratic dispersion, but if I take it like this, so this my field states, and there is no word about where it's half filling. I even consider isotropic system, so there is even no lattice here.
Yeah, but somehow you.
2pf is this. This is pf.
Yeah.
And this is minus pf. 2pf is the momentum transfer between these 2 points.
Yeah, but in your expression of a theta, there is u of pi, and yeah. So I assume that.
Pi is momentum transfer to kf.
Oh, that's the theta.
This theta.
Okay.
This when I say u of pi means u of theta equal to pi.
Okay, I see.
This is u of theta equal to 0. U tilde, u tilde. U tilde is a function of theta.
I see. Yeah.
Right?
Yeah, I thought it was a function of k and the.
No. It's a function just of angle. Very good. With all this, let's see where this one of L4 comes in. Well, It comes from the fact that if we write down integral over solid angle of theta over 4 pi PL of cosine theta and P tilde particle whole of theta, we get MPF over 8 pi square and then minus 1 to power of L divided by L force. That's precisely what we have. This is where 1 over L to force comes into play. I already mentioned this, but this gives you exact result, how it goes. Without singularity in the derivative, you will not get this result. And it's something that I will formulate the problem for the homework later, but this will be part of the problem. For any regular function, it will be exponential. Very good. Now we are ready to play the game. Because we said, I don't know what the interaction U of Q or U of theta is, or U tilde of theta. It's a fully dressed interaction without any non-analyticities. It's analytical interaction. So there is some U tilde of theta, from which I only need U tilde of 0, and U tilde of phi. Right? Here are the results. I have A, I have B. This I actually even don't need because I had that expression. So then we can write down immediately expressions like this. That, first of all, I need good eyes from you. If I take this guy and I expand this function as a function of theta, and then I shift theta by pi and expand again, and then sum them up. Which components will contribute?
Even.
Even, good. And if I do it here, odd, right? So one term will give me only even components, one term will give me only odd components. So what we will get as the result is this. I'll erase this part and write down the results. The results are A. Now I want components. AL. I take this guy and expand in Legendre polynomials, and I want to look at large L. So L will be large. This is how in formula which I just erased, I get 1 over L to 4. So it's of course only valid when L is large. But L is equal to even, this is 2m, and will be equal to 2 U tilde square of pi minus 2 U tilde of 0, U tilde of pi minus U tilde square of 0 times MPF over 8 pi square, 1 over L to 4th power, and BL equal to M plus 1. These are odd components, will be equal to 2 U tilde square of pi minus twice U tilde of 0, U tilde of pi, now plus U tilde square of 0. And again, with minus sign, it will be MPF over 8 pi square, 1 over L to 4th power. Very good. So here we are. Again, beauty here is that I didn't say a word about what U tilde is. It's some interaction, infinite set of graphs. It's not perturbation theory. It's not actually second order. It's I incorporated all regular normalization into some unknown function, right? Very good. Now, we look at this and we look at this. And remember what we need? We need now we take components. These are components of our dressed U in spin triplet channel. This will be components of our dressed U in spin singlet channel. And we need at least one of them to be negative, means repulsive. So it means attractive, right? Let's see. Good thing, first of all, let's look at this one. These are spin singlet components. This is positive, and then we really don't know what it is, right? Because this term is with plus sign, these two terms are with minus sign, so who knows what it is? I can make it positive, I can make a negative by making different interactions, right? We cannot make any statement, right? And now look here. I need to close the bracket like this. Overall sign minus. What do we have here?
It's a square.
Sorry?
It's
It's sum of the two squares, right? It will be u tilde square of pi plus u tilde square of pi minus u tilde of 0 square, right? I don't care what u tilde is. This is definitely sum of the squares. So this is definitely positive. And as a result, BL equal to m plus 1, meaning odd components for spin triplet pairing, they go as minus some number divided by L to fourth power. This is what is called Kohn-Latinger accurate calculations or Kohn-Latinger theory. It tells you that in an isotropic system, no matter what interaction is, there will be attraction, definitely, in odd channel with large angular momentum. How large? Who knows, right? But large. When 1 over L force with whatever coefficient is here will be larger than e to minus L coming from a regular interaction. So as a matter of principle, it tells you that it doesn't matter in isotropic system with, if we don't include any frequency dependence, assuming that is completely irrelevant, then statement is that any isotropic system is the superconductor. For repulsive, for attractive interaction, if you manage to get attractive interaction, of course, bare interaction will be attractive and you don't need any corrections. But if you get repulsive interaction, then you are guaranteed that these components are attractive. And it's more than one, definitely, right? So this closes what is called Kohn-Latinger theory. Before I go to what's called Kohn-Latinger computational procedure, let me say one phrase about what will be homework. This is very nice based on the fact that particle hole polarization, P tilde particle hole, had a logarithmical singularity at 2kf, or 2pf, sorry, keep calling it kf. If we are in two dimensions, and we deal with free formulas, that's important, if we deal with free formulas, then we calculate polarization P tilde particle hole as the function of Q. I put it like before as a function of Q. This is your 2pf, and you find that it's a constant. It has singularity, it has square root singularity above 2pf, but we need only this part. This is true if the dispersion of the fermion is k square over 2m. So for parabolic dispersion, it's a constant. And that was a problem to a certain extent because of these things. Then I want to do exactly the same, but there is nothing. Interaction just have no k, no momentum. Right? So which means that all components of angular momentum with L not equal to 0 are just simply 0, right? So I get nothing.
It turns out that this is an artifact of dealing with free fermions. When you dress up fermions, you start getting something, but it becomes more involved problem. I forgot to mention that there is sharpness of this result in 3 dimensions. Namely, I did calculation for free fermions. You can do calculations with dressed fermions, but because everything comes from tiny vicinity near the Fermi surface, as long as fermions form what is called Fermi liquid, meaning that, as Nikolay already described, their green function will be Z divided by omega minus, say, P minus PF divided by M star, the result will be the same. There will be no change of the result. Yes, there will be Z as the overall factor. It will come here. Somehow M star will also affect the overall factor, but nothing will change 1/L to forced power behavior. So this is really universal result. For 2 dimensions, this special situation, which people so much discussed in recent years, more than necessary, is the property of K-square dispersion. The question is, what happens when the dispersion is K2 Let's put it alpha K2. You may say, well, it's artificial result. No, it's not. In the graphene sheets, which is called now 2-layer graphene, 3-layer graphene, 4-layer graphene, pentalayer graphene, if you put a displacement field, you start splitting the sheets, and at the same time, you make dispersion more flat than original one. So K4 dispersion is completely realistic situation in what's called Bernard bilayer graphene or rhombohedral 3-layer graphene, etc. So question. We have 2 dimensions, have dispersion alpha K2. What happens with Kohn-Latinger? Part of the calculation is to prove that if you have any regular interaction, then at large angular momentum, right, it will be e to minus L. And if you have non-analytic function in 2 dimensions, it will be 1/L cubed instead of 1/L to force power. But I want you to look at the dispersion. Take alpha positive. Let's look at electronic dispersion. Dispersion goes up. Question, what will happen? Will you get Kohn-Latinger superconductivity? And if you get it, in which channels? And you can do calculations in 2 ways. And this will bring me to the second part of this point. I want you first to do calculations exactly like this, to find out what happens near 2KF. Is there any non-analyticity of the response function of particle-hole polarization near 2KF? And I'm pretty certain there will be non-analyticity. Then exploring this non-analyticity, you can do all calculations of this kind. That's number 1. The second part related to how people nowadays treat Kohn-Latinger. Because it turns out that Kohn-Latinger is a step towards what is now in modern literature is called pairing by spin fluctuations, pairing by nematic fluctuations. It's all originate from this. But in order to understand these things, one needs to relax accuracy. So far, the calculations which I described to you were really accurate calculations. There was, again, assumption is that besides non-analyticity in a particle hole bubble, all other normalization will give you something regular. This was the only assumption.
You have another one.
Sorry?
You have another one.
Which one?
That the interaction decays with frequency. And if the actual story is that, well, for Coulomb gas at least. The real story for Coulomb gas is that for large L, the interaction is increasing with frequency. And this Kohn-Latinger effect related to Fermi is 1 part in a million to what you get from frequency dependence.
Right. If you only do renormalization in a
just all 4 diagrams.
Maybe.
For large orbital channels,
Mm-hmm.
this happens at small RS.
Yeah.
When the perturbation theory is okay.
Yes.
In large orbital channels,
Uh-huh.
produce superconductivity.
million times stronger than Kohn-Latinger 2-Kafemi single.
Okay, I didn't know about this.
No,
Fine.
everything is correct as you said for statics.
Sure.
The moment
I
that
understand. So
dynamics comes in.
So I think
million
that
times
assumption that interaction is weakly decaying function of frequency may not always work. That there are cases when interaction is increasing as a function of frequency. And then you can get superconductivity for reasons that was described in the previous slide. I assume that frequency dependence is irrelevant, but if it's relevant, then you put it in. Okay. Now.
So
yeah.
you assume this U of theta.
Yes.
So, and you said that U of theta should be analytic.
Yes.
That's it? There is no other requirement?
There is no other requirement.
So
no.
0 or pi, I mean, why you choose the 0 or pi as a dominant contribution?
Because this is where non-analyticity comes from. Because this is where non-analyticity is. I try to explain this with the answers. That when you look where non-analyticity comes from, it's only forward scattering or back scattering. There are no other terms which give you non-analyticity. Okay.
Question: Is there any reason you didn't include vertex correction?
On the load.
Is there any reason you didn't include vertex corrections? Are they just less relevant? Or
Well, one has to be careful when the word vertex corrections. In some sense, I did include vertex corrections because one of these wine glass diagrams in the conventional notations are vertex correction diagrams. So these are just 4 diagrams that give you one. These are diagrams that give you one singular particle Hall bubble. You may ask different question. What about diagrams with 2 singular particle Hall bubbles? They exist, but they give you 1/L to 8 power, etc., etc. So in terms of non-analyticity, these are leading diagrams. And 2 of these diagrams are technically vertex correction diagrams. Okay, let's move on. And when we move on, the story goes this way, that it's pretty common, starting in fact very quickly after the original paper, to say, okay, let me try to do the same but differently. I don't want to look what happens at large L. This is nice problem for theorists, but has no practical relevance. We want to look what happens with P wave, D wave, etc. And then you can do the thing. Instead of saying what I said about accuracy, etc., you just say, okay, let me just do second order. And with this, let me assume that there is some Hubbard interaction. This by itself a big assumption. I neglect all frequency dependence. I neglect original momentum dependence of Coulomb interaction. I assume that there is a regular screening. Regular screening is strong. And this regular screening gives you interaction, which the first approximation is like Hubbard. Hubbard U is interesting interaction. Because it's constant, if I take this interaction and view it as function of momentum transfer, it's not a function of momentum transfer, it's a constant, right? So if I take Fourier transform, not Fourier transform, if I take angular momentum component of this interaction, obviously interaction UL equal to 0 is non-zero. And let's assume that this fully repulsive, so this completely repulsive Hubbard interaction, while all components with L not equal to 0 are exactly 0, right? So obviously we have a constant interaction, a repulsive interaction, and this one. And then what people do and started doing starting from middle 1960s is to say, okay, I want to calculate the quantity which I kept in this corner for a while. I want to calculate this irreducible interaction. It was in red color before, right? And I just do it to second order perturbation theory. Just simply second order real perturbation theory. Then all the diagrams are the same. I get this plus all other diagrams, but now this one is Hubbard U. Simply Hubbard U. Which means U of 0, U or pi, they're all the same, they're equal to U, right? Yes.
In this case, we'll also include the Bayer diagram because we are not at large L anymore, right?
Yes, but we want to do it in a funny way. We have to. But the game here is that with perturbation theory, I will not be able to overshoot this one. This will be the largest term, it's perturbation theory. Second order will be small. What I hope to get is these guys at second order, the ones that were originally zero. And then the story goes that yes, you do these calculations. Now it's completely conventional perturbation theory, just brute force calculations. And you find the interesting result that we call it U tilde, right? This interaction which is irreducible for particle-particle channel. We calculate U tilde L, which is of course proportional to U squared, right? To first order there was nothing, we go to second order. And it's some function of L. With all coefficients, of course, MPF over 2 pi square are there, but we're interested in this function. First question, this is basically referring to your question. F of 0 is positive. So we make interaction even more repulsive. S wave is completely out. But it turns out that if I plot F as a function of L, of course, there's discrete points, right? 1, 2, 3, 4, etc. So I have to plot it. And when I do this plot, this was positive, and all the others were negative. Starting from L equal to 1. And which means that they're all attractive. Again, accuracy. Well, second order, it's something small, right? So you expect that, of course, dimensionless coupling constant will be like U squared will have quadratic smallness. Nevertheless, they're all negative, attractive. And you may ask, out of this attractive component, which one is the largest? This one, L equal to 1. And this resulted in the statement, which I don't like that much because it's not very accurate statement, but nevertheless folklore is this, that if you take Hubbard model, if U is negative attraction, then you get S wave. Don't ask me a question how to get it negative. If it's negative, then you get S wave. If it's positive, you get P wave. That's how the story goes.
Question?
Yes, please.
Does it have anything to do with like if you have a positive U, that's like a ferromagnetic critical point which supports this spin triplet superconductor?
Yes, but we'll need to go to lecture number 3 to see it. It is absolutely true. So this is the first step towards what is called pairing by magnetic fluctuations. And in this case that you are talking about, this will be pairing by ferromagnetic fluctuation. Yes, I will come to this point, but at this stage, it's just second order. You cannot see anything from here. Okay. Now we play a little bit a game. Because this all is wonderful if we don't ask a question why we restrict with this, but still, it's a pretty powerful statement, right? But real systems are lattice systems. So this is good exercise for helium-3. Yes. For helium-3, this was well exercised. Think, okay, I already told this wonderful story. Let me take 30 seconds and tell the story. It's really a story about how people in 1965 were too earnest. When Kohn-Lattinger did their calculations, they had formulas, right? And the formula was UL tilde was something divided by L to 4, so it is 9 minus, and this is L equal to M plus 1. So you need to do something with this formula, right? You want to publish it. So you need to apply. So they did apply the results to helium-3.
for reasons that nobody wants to know nowadays. In 1965, community believed that the pairing in helium-3 would be with angular momentum equal to 2. So what they did, they said, okay, they take what Nikolay and also I discussed, they expressed interaction in terms of scattering amplitude, just simple leading order, linear relation between U and scattering amplitude, said that suppose that besides they took Hubbard U. Said let's express interaction in terms of scattering amplitude. APF in helium-3 is close to 2, so they knew the number, so they claim let's substitute and get TC, I guess 10 to minus 40, something like that. Something like this. Which everyone said great, wonderful result, and yeah. It turns out that, of course, a few years later, people found that pairing with helium-3 is with L equal to 1, and TC is ordered 2.3 millikelvin. If they took their formula, the ones that they have, they presented formula. There is one tricky thing, prefactor, right? You do everything to logarithmical accuracy. You don't know the prefactor. But they had formula with prefactor Fermi energy. So they had formula for TC. This I put interactions, then you need to put this interaction in the particle-particle channel, do a standard logarithm, and obtain TC. So they obtained TC, as I said, 10 to minus 40 times Fermi energy. Something like this. If they just substituted L equal to 1 here instead of L equal to 2, just into large L expansion, simply without even calculating the full result accurately, they would obtain TC of order of 10 to minus 3 times Fermi energy. And Fermi energy is Kelvin. So actually 2.2 Kelvin, right? So if you formally substitute, you will get this. Which means that basically it's a story like you have a formula which you can only apply for large L, but you want to apply it to L equal to 1, right? Nowadays, I guess everyone will say, if L equal to 1, here is what I get. But they didn't do it. Yeah, it's interesting how people restricted themselves at that time. Yeah. So anyway, 3 years later, already after superfluidity in helium-3 was found and L equal to 1 was established, Fein-Lauser did the same calculations for the Hubbard model and obtained TC 10 to minus 3 Kelvin. But this is a posteriori consideration of already known, or attempt to understand and explain already known experimental result instead of predicting it. Okay, in the remaining 10 minutes, I guess I have, right? Here's some people like, yes. In the remaining 10 minutes, we'll play a few simple games. And then next time we'll do a normalization group, and then we'll discuss something that goes beyond Kohn-Latinger perturbation theory. Game is this. It's all great, but this is an isotropic system. What happens if you put a system on a lattice? If you put a system on a lattice, you cannot expand in angular momentum. You cannot have infinite number of orthogonal wave functions or of orthogonal representations. What you have on a, say, square lattice is 4 one-dimensional representations and 1 two-dimensional representation. Each contains infinite number of eigenfunctions, and pairing problem does not decouple between this eigenfunction within each representation. So technically, pairing problem on a lattice is infinite set of coupled equations. People make approximations saying that yes, true, but we close our eyes, take the first harmonic in each representation and forget about everything else. But technically, we cannot do. As a result, statement like this does not exist. Even if you consider interaction as Hubbard interaction, you cannot say that it will be either S wave or something else. In other words, there is no statement that any system will become a superconductor eventually. And we know examples on the lattice when even theoretically system does not become a superconductor. Nevertheless, despite all this, the fundamentals of Kohn-Latinger idea came into play in lattice systems. And fundamentals means don't take bare interaction. Bayer interaction, again, with the risk of simplifying things a little bit more, let's assume, and just in our discussion, let's assume that we deal with Hubbard interaction. So the statement is don't take Hubbard interaction. If you want to look at the pairing, look here. Calculate the fully reducible interaction in a particle-particle channel, which means include renormalization of this interaction in a particle Hall channel, just like we did on a lattice, in the isotropic case. You can do it on a lattice. If you do, you cannot do it like Kohn-Lattinger did. Very accurate large angular momentum, because angular momentum is just, again, 4 one-dimensional representations. It's 0, 1, 2, 3, 4, 0, 1, 2, 3. That's it. But you still can do perturbation theory. And the same set of diagrams, like this one plus this one plus the other two, plays the same role. You can take lattice system, you can calculate now lattice version of polarization bubble. Again, let's assume that this interaction is nothing but U. You get effective interaction, which will have some non-zero terms in the channels with non-zero angular momentum. For example, in D4H in square lattice, you get 4 one-dimensional representations. That's called A1, B1, B2, and A2. This is like S waves. These are 2 different D waves, and this is, I guess, is G waves. You start with saying there is repulsion here, but you don't know anything about other channels, including D waves. And so the question is what you get when you do the normalization of the interaction. And this is where 1,000, if not 10,000 papers over the last 20 years appears about studying cuprates, pnictides, heavy fermion materials, and in recent days, twisted ditch alkagenides, and before that, twisted graphene, which is the same story all the time. You start with Hubbard interaction. Some people actually said, let's consider static screen Coulomb interaction or gate screen Coulomb interaction. There were also papers like this, but the story was always the same. Let's calculate leading renormalizations. Let's see whether we get something in a channel which will be not conventional S-waves. And I will give you just 2 examples. One will be important for me when we move next time to the next lecture. So one example that everyone knows about are cuprates. Doping, Hall doping, electron doping. So let's call it electron doping. This is Hall doping. Magnetism is here. This is temperature. Superconductivity is here. Let's call superconductivity with different color. Superconductivity is here. Superconductivity is here. And in fact, it's vertical boundary. This Martin result. And there is, of course, wonderful pseudo gap that exists here, and a lot of studies is about pseudo gap. But the question is, do we know what is the pairing symmetry in cuprates? And to a certain extent, I would say, yes, we know what's the pairing symmetry in cuprates. By the way, Buckley Prize was given for establishing pairing symmetry on the cuprates. And it's D-wave. So it's both cases, symmetry of the superconducting state is D-wave. What D-wave means in a simple language of lattice systems. Let's look somewhere here where all non-Fermi liquid physics that is so much discussed in this range is not that important. What it means? It means that quantum oscillation measurements, the ones that they measure the size of the Fermi surface, very accurately tells you that you have Fermi surface, which is called open Hall Fermi surface or closed electron Fermi surface. This is occupied state. Normally, we used to write down our Fermi surface like this, and occupied states are here. This is our closed electron Fermi surface, right? This is open electron Fermi surface. I probably misposed it, says Hall. This open electron Fermi surface. These occupied states are all here. Empty states are here. Very good. So just from electronic structure. And by the way, this is not theory, this experiment. Experiments very nicely found this Fermi surface and found that the area of the Fermi surface satisfy Latinger count. So the density of electrons is proportional to the area of the Fermi surface with the exact coefficient, which is what's known as Latinger theorem. You know what's Latinger theorem? It's basically a statement like this. It's a wonderful theorem. It's very non-trivial theorem, and you mentioned this theorem at the first lecture. But in some sense, it's like this. You take free fermions and calculate the simplest thing. What is the volume or area in 2 dimensions of the Fermi surface which can accommodate n fermions? Well, each level is occupied twice, up and down spins, and you do trivial calculations and calculate the relation between density and area, right? So for free fermions, Latinger theorem tells you that the relation is exact, that exactly the same relation holds for interacting fermions, that all corrections from the interaction cancel out. This is what Latinger theorem is. It's wonderful for experiment because you know what the number of electrons, you know what you measure the area of the Fermi surface, and then you ask the question whether the two are related. Yes, they are related. So this is no doubt that this is Fermi liquid. With this Fermi liquid, you can look into where the density of states is the largest, because don't forget that the coupling constant for superconductivity is proportional to the density of states. So you obviously want to look in the region when density of states is the largest. They are largest in the corners. So we are mostly interested in what happens in the corners. And then we can look at the corners, and we look at spin singlet superconductivity. D wave belongs to a channel which is spin singlet, right? S is singlet, P is triplet, D is singlet, right? Next triplet is F. Yeah, F. Okay, so what is D wave? D wave is when the gap is delta here minus delta here, and then because it's spin symmetric, sorry, it's momentum symmetric, this one and this one are the same, this K and minus K, this is delta, this is minus delta. The gap changes sign twice when you go around Fermi surface, and because it goes from minus to plus along the same arc of the Fermi surface, it necessarily has 0 in the middle. So this gap necessarily has 4 zeros. And this is another beauty of D wave, because then you can study physics associated with the nodal points and many, many different things. So it's, I would say that practically no one has doubt that it's D wave superconductor. People discuss why, but D wave is pretty well established. Very good. Now, what Kohn-Latinger type? It's not Kohn-Latinger, it's Kohn-Latinger type or Kohn-Latinger inspired scenario tells you about this. It will tell you this, that let's play a really simple game. Let's take situation when we assume that there is a gap delta 1 here and delta 2 here, and then because it's spin singlet, it's still delta 1 here and it's still delta 2 here. And introduce 2 interactions. One interaction will be like this. So let me just, yeah, I will be done in 2-3 minutes. Let's assume that fermions near this corner will be solid lines. Fermions near this corner will be dashed or black and blue. So I want to introduce 2 pairing interactions. One will be like this. Of course, it will be K minus K goes into P minus P. But what I mean is that fermions are near these 2 points only. They don't move far away. They're close to this region when the density of states is large. Or there is another possibility. I take 2 fermions from one region, solid region, and transform into 2 fermions in dashed region. This is called pair hopping. I can do it, right? This is K minus K, this is P minus P. Only K, sorry, let's put color. K is close here. This is where K is. Obviously, minus K is here. And P will be here. So Nikolay already showed you how to solve this problem. You basically have to solve 2 by 2 problem for the pairing gap, right? You want to check whether or not your susceptibility will go to infinity or your eigenvalue will go to 1. And let's call this interaction U1 and let's call this interaction U2. Very good. You can write down 2 equations. Delta 1 is equal to something delta 1 plus something delta 2, and delta 2 is equal to something delta 2 plus something delta 1. Something contains Cooper logarithm, of course, and this interaction is U1 and U2. And you can immediately check that if you sum these 2 equations or take a difference between these 2 equations, you get 2 decoupled equations. So one equation will be for the quantity delta 1 minus delta 2, and effective interaction in this channel will be U1 minus U2, or it will be for delta 1 plus delta 2, and effective interaction will be U1 plus U2. You can do it very quickly. It's just solving 2 by 2, right? Very good. Now, story goes like this. We deal with repulsive interactions. U is positive. U1 is positive. U2 is positive. What is this guy? This guy is obviously positive, right? So no way we can get anything in this channel. So out. But here, everything depends on what is larger, U1 or U2. If U1 is larger, you don't get anything. If U2 is larger, you get something. What you will get if U2 is larger? We didn't get anything here. So the only solution which we can get will be when delta 1 plus delta 2 is equal to 0, right? Which means delta 2 is equal to minus delta 1, right? So we get exactly what we want to have here. So then what I say is that it gives only 2 options. Either S wave, this is obviously S wave, right? Delta 1 equal to delta 2, gap which is the same everywhere. Or solution in which gap changes sign between these 2 corners, necessarily have 4 zeros in between. And then Kohn-Lattinger inspired story goes like this. Let's start with Hubbard interaction. If we start with Hubbard interaction, then U1 is equal to U2 is equal to U. We get U1 plus U2 obviously equal to 2U positive, but U1 minus U2 is 0. We go back to exactly the same story as we discussed 10 minutes ago with respect to isotropic systems. We get repulsion in S-wave channel. We get 0 in D-wave channel. So what we want to do? We want to go to second order, write down all these 4 diagrams, and ask what these 4 diagrams give you for the normalization of this guy and for the normalization of this guy, right? Completely straightforward procedure, right? For example, here you will get, sorry for using different color, you definitely will get this. You will get polarization with momentum transfer between 2 corners, right? By lattice symmetry, this momentum transfer pi pi. While here, you will get polarization with momentum transfer close to 0, right? So then you ask a simple question. What is larger, momentum transfer polarization bubble with momentum transfer pi pi or polarization bubble with momentum transfer 0? It's completely straightforward calculation, free formulas. You just calculate polarization bubble. And short answer is U2 becomes larger than U1 to level U squared. So let's say it, and then we'll continue next time when I give lecture 3, which will be on Thursday. We do second order calculations, starting from assumptions that there was nothing in D-wave channel, and it turns out we get attraction in D-wave channel, right? It can be done in 5 minutes, less. You just calculate 2 static polarization bubbles. As the consequence, we immediately find out that at least here, superconducting gap will have 4 nodes on the Fermi surface. This is the work of 3 experimental groups for which Buckley Prize was shared some years ago. Pretty established result. Let's stop here. And then we ask a question. And what if I don't play this game? What is with some screen Coulomb interaction? Then you can say, well, no question. This guy will be larger than this one. Look, this interaction with small momentum transfer, this interaction with large momentum transfer, right? So then I would say that you start with the fact that U1 larger than U2. Second order perturbation theory will not change. So then we have a problem. And next time we'll solve that problem. It turns out it's not a big problem. Yeah. Okay, stop here. Let's move.
We have sometimes question in the isotropic Kohn-Latinger. What is the main contribution? So, in these new approaches, usually people use that just the direct RPA or direct exchange and so on. What is the main particle hole diagram that contributes to the
What I described as Kohn-Latinger, everything comes at second order. I will say a few words about this. It's a special situation, for example, in tungsten selenium-2 twisted. You find out that there is a higher order Van Hoff singularity, and again, you play the game with this one. But so far, I just said second order. Logic will be this. Next time, we'll see what happens when there is another channel that competes with superconductivity. It turns out that it helps, enormously helps. Even when you think you cannot do perturbation theory, it turns out that you can extend it to regions where normally you shouldn't. And then we find out that this is nothing but intelligent way to say pairing mediated by spin fluctuation. And this will be a step towards summing up infinite graphs. And in this case, it will be summing up maximally cross diagrams. You can also sum up diagrams in a vertical channel. Then you will, this is a way to, for example, find the pairing mediated by pneumatic fluctuations. So there are steps away from second order. But second order is a base for all of this. And in order to do this and justify, you can always do this with question that you don't justify what you're doing. So in order to justify, you need to find competitor. It turns out that it's called competitor, but it's not competitor in reality. It's something that just absolute conductivity.
Yeah, sorry.
Any other questions?
I'm still having a tough time understanding the difference between U1 and U2 and those two diagrams that you have.
Yes.
So so you say that there are Van Hoff singularities at 4 points on the cube.
No, I'm just saying Van Hoff singularity. I'm just saying increased density of states.
Okay, so at those points, and then you define U1 as interaction between points which have the same order parameter along X and U2 along.
No. I defined U1 as interaction when these two fermions are both close to this point. They're in the region, in the vicinity of this point. I define best fermions as the one close to the vicinity of this point. What I didn't write, for example, is that this interaction is also U1, right? This interaction with small momentum transfer, this interaction with large momentum transfer, but both are pairing interaction. Both are K minus K goes into P minus P.
I have a question. So in your second order diagram for KL, the bubble diagram is cancelled by the 2 1 years diagram.
I decided not to talk about this. Yes, for Hubbard U, for U, there is some cancellation between this diagram. It's detailed.
Your question?
Yeah.
So these KMP are like relative to the patches where we expanded from.
Say it again.
I mean, these KMP from your diagrams are like expanded near the red spots on what you draw over there, right?
I still don't understand. Sorry.
I mean, these KMP
Yes.
are relative to the red spots you drew over there, right?
They are close to the patch that you have.
They are close to the patch.
Yeah.
They're close to the patch. So this is one. It's actually, yeah, this is patch here, patch 1, patch 2. There came here, all fermions close to patch 1.
One is next to pi 0, one is next to 0 pi. Let's put it this way, right?
Yeah, sure, but
So in principle, we can also draw that, let's say, exchange diagram.
no, this is this lowest order. There's no exchange here. It's a lowest order diagram. When you do the normalizations, of course, you write down exchange diagram.
Oh, so you only write down things in the Cooper-Chen.
No, what I mean is this. If you want to write it something like this, you have no other choice, because if this is K, this must be minus K. It's only particle-particle channels that we consider, right? So you're guaranteed that these two are solid lines, right? These two can be solid or dashed, but you cannot have the solid dash solid. This doesn't hold at this level.
Okay, we can say thanks to the.
Is this, I gotta go.
If you were talking about superconductor, and also. What we are essentially using is also.
I got this number well enough. I can see.
And you can do this only for shopping. Your interactions are more.
Yeah. Maybe never.
First things,
Should be there.
Sure. It's W line. I will just put the bubble in the middle.
What is
Problems.
И потом посчитать от нее.
Да, ну короче, посчитать поляризационный оператор.
Сделать преобразование лежа.
Понятно. Доказать, что преобразование
Сделано, выглядит чуть как. Ну, за вечер решить можно.
Ну вот сетап.
Что?
Сетап готов.
Посчитать надо, посчитать вот это.
И вот the point is just was neglecting frequency dependent.
Я probably have a bigger graph. Ты записал, я понял.
Да, вот ведь, а вот
вареников.
Да, что вареников.
Я думаю, все-таки обратно людей трофать на такси в виде Джейсона.
Сейчас нахерачимся вареников, и как раз можно эту бабл посчитать, то, что надо. Вареник.
Ой, ща я посижу и пойду тебя спрашивать.
Да, я пошел это. Сам торговать просто.
It's correct about the questions about. Let's assume the frequency dependent
on this, what's the number into.
Yeah.
And just saying,
Let's check
I
this.
think I remember your survey.
Strong reflection.
But if they count as a pairing,
It's one of the inventions.
a certain type of pairing, or? Yeah, so that was.
How you could draw
So they normally say how you address these J equals 3 halves, and basically you can define Jx, Jy, and Jz. You can write down an inner product of J with K. The Hamiltonian, the non-trivial part is divided by that equation.
Very late.
But then in addition, I did write down an assumption for the pairing state. Really carefully justify where that came from. I just assumed we had a pairing in a particular channel. Shows, I imagine we had local attractions that were attractive, so like attractive view, but not in the.
It was an electric charge.
In these Jacobs we tested. So I just had more,
This is
more intricate.
No, if you want to define the Hamiltonian, in terms of the Hamiltonian, there is like.
In general, there will be a U and a V. Everything is spherical, will be just those two parameters. I think what I've said is
Screen, however, people will like to direct to the ionic charge.
Can you see the board?
Pairing states in there. I'm gonna choose one particular linear combination as my pairing. And so the idea was that there I can stabilize an XZ plus YZ state, and I know a little bit about factoring the superconductivity. So I said, okay, we can study that.
Okay.
Yeah, so it's not. You can do a better job. You can say, well, we don't have spherical symmetry, maybe we have cubic symmetry, this is a good representation. And you can show that this channel will certainly be doubly degenerate, and there's only two characters. So you get separate interactions for all these. Spherical. Basically, you probably heard in like in a cubic system. T2G plus G. Also have their own separate interactions, and then what we're doing. Yeah, like crystal field effects, exactly. It's the EG channel. And that's in essence what we've done, but we've made the algebra simpler by making frequency.
Say we assume some symmetries. Choices of pairing.
Yes, absolutely. So I talked to the statement is no matter what choice pairing you have, the gap is either something that's fully gapped. Then, but then you want to identify the cases where you have lots of buffer.
It's not so.
I guess I was trying to get into more about the maybe and earlier, so I guess quite new, but so sometimes people would focus on, for example, spin triplet.
Yes, often, yeah.
Also, focus on, say, chiral superconductors.
Yes, that's right.
But in these two these two different, for example, the first one focus on the pairing.
Yeah.
The second one so one thing I asked was, for example, in the chiral superconductivity, let's say in this chiral superconductivity, do we?
Okay, that's fine. That's perfect. Yeah, thank you.
Yeah, so at least the question I asked myself was in this.
And then there's
the potential of a chiral superconductivity then. What's the example?
Oh, I see.
This type of question. So I was trying to, I don't know, maybe unify sort of.
Oh, I see. Okay.
So let's say, for example, one thing people discuss a lot was this. So just by proximity.
Yeah.
There, people also discuss topological superconductor and ask what's the parents say that topological superconductivity and. Obvious answer?
Yeah, I see. You see something that's meant to be a topological superconductor. It's not clear what even is the pairing state, is what I'm saying. Yeah, they don't say this, they just say, yes, so simple. Yeah, it does become subtle. So for the example where you proximatize a topological insulator, there you're using the fact that you have strictly speaking, your topological insulator states are, well, it breaks inversion symmetry, and so you have two states of a spin orbit coupling, right? And the spin orbit coupling is an important part of the topological surface state. So now, like in our classification, you fall out of the stuff I discussed and go into a new class there.
Yeah.
And then what you find in practice is that singlet and triplet mix. And then you can write down sort of an arbitrary linear combination of singlet and triplet parameters. But you can go more triplet or more singlet. And we don't know most of these theories where you get these states, you play. This is the direction.
What is this branch?
It's just triplet. Going out there.
Okay.
So
With the trend.
Anywhere, some branch.
Well, this is that.
yes. In this case, yes. I mean, it's not so straightforward to say what I said exactly right, but there is a way.
Nothing happens.
There is a way of understanding it that way. So somehow loosely speaking, the triplet part becomes important. Yeah.
If it was.
And they do generically need to have that. Not full degenerate states. But you have to split that critical part to a lot of superconductivity, you know, my own states.
Right. It's another thing, like, I guess, at least what interesting to me, especially, so focus on more on, what type of signatures we could potentially work
Oh, I
on.
see. Okay.
So, at least nowadays I focus more on time versus symmetry break-in, superconductors, and you can do so by doing experiments like,
For this particular.
That seems to be actually, I like that probe right now, it's just a little bit different than polar curve, but.
Right, exactly.
Yeah.
That's why I've been working on a lot. So, for example, one work I did was in this iron terrorist cell 9. Then it was like kind of like the example I the self proximity, and these people argue that it had the band topology that hosts this topology.
Oh, I
later
see,
on
okay,
state.
and then the states are self-proximate, I think.
Right, and then the question is that how do we break the time versus symmetry to generate this Majorana bounce state?
I see, okay, yeah.
So we did some work from this actually we can place them on top of each other. So at the interface we can form a Josephson junction between. You can probe the Josephson diagram. That is field free.
So I know your paper, actually, yeah, I do, so did you publish it in Nature Communications?
Yes.
Yeah, okay. Yeah, and I was.
I'll talk about that in my poster.
Okay, so I know, so. Yeah. So I know it for a strange reason. I don't know if you know the story, but so a lot of people have been asking, why is it in, you know, some of these iron-based materials like cerium and sometimes selenium or not selenium, but with sulfur, or cerium doping, you see broken time versal symmetry.
Right.
And there was an explanation put forward by Libor Shmechko and Igor Mazin that simply said that
ultramagnetism.
Well, yeah, it is ultramagnetism, but it's not really. Yeah, so it's an antiferromagnet on the iron sites. So, and that antiferromagnet has this property that it breaks time reversal, it breaks inversion, preserves their product. So you have a TI symmetry in the system, so it's not an ultramagnet because you have a two-pole degeneracy. But now you add an interface, and that interface breaks the inversion, and so hence you do have a splitting of states, and then you can ask. And then you can ask, what is the structure of that? And in spin space, it's an ultramagnet.
Yeah.
And so the idea is indeed that you have an ultramagnet there coming from this underlying antiferromagnet and the substrate.
Yeah.
So I did some work on these states as well and found that even without the ultramagnetic part they're talking about, if you just have this structure, it actually generates spontaneously in that like phase. So this is dictated by symmetry. Allows you to write down a finite Q pairing state that is stable at 0. And so,
That's actually, I think our, at least my theory, colleagues discussing that possibility
exactly.
also, and when I find momentum.
Yeah, and there the mechanism you guys suggested was that you have broken time versal symmetry, so there is some field created.
Yeah.
And that field created can push the superconductor to an FFLO state. But in the picture I'm describing, you actually automatically get the FFLO state the second you have this antiferromagnet. I mean, the key is that you need the moments in plane for this to be true, but you do have it. It's guaranteed by symmetry to have it. And so you didn't have this issue that FFLO, you need kind of a certain right range of magnetic field strength. Because if it's too big, you kill the superconductor. If it's too small, it's no FFLO state.
Yeah.
But here, this is generated by symmetry. And so whenever there's superconductivity, it must be FFLO.
Yeah.
So that was, we pursued that. I mean,
Was the model a 2D on the surface or it required the interface?
it didn't require the interface, no, but it came from a
2D surface.
Yeah, it was,
This one,
I mean, so, yeah, so it was actually,
It's existing, it's what happened.
the experiment was from Chubukov.
I think they look at they did muon.
Yeah, they did muon.
Yeah, and show time versus signature break-in potentially.
Yeah, and so then we tried to give an explanation for the Bogly-Bott Fermi surface. And then, I mean, to get that, you needed to break time reversal symmetry as well, of course. And we suggested this anti-ferromagnetism would do it. And then we automatically got this finite momentum carrying state. And so it's a lot like your picture, except the only advantage it has is that whenever there's a superconductor, it's finite momentum guaranteed by symmetry. The disadvantage it has is that you need this antiferromagnetism to show up.
Right. So how do you put in this ferromagnetism
In the theory? Yeah, I mean, actually, we have analogs and altermagnetism, so you'll see it show up in probably the fourth lecture. Yeah, actually, so some of it I can explain more easily.
Oh, yeah.
I start writing down the Hamiltonian.
I see that,
I can start showing you, what relates to that.
Yeah, I think that's very interesting because at least to me, so how I see our experiments, there was, so I made that device that allows us to probe this transport property, which is a superconducting property. It's superconducting.
Yeah.
But compared to other probes, which I've looked to, people try to show this time resistance break-in. I think the epicenter magnetometry optics. These are like technique, which take a snapshot. And I try to see magnetism. They just see magnetism. The general material property. It doesn't necessarily have to couple to the superconductivity. But in order for superconductivity to shine, it really has to do something.
Yeah.
Otherwise, if they are separate in region, that would not do. So I see it as a titles, sensitive symmetry probe. I see as a superconducting concept. I think that's its uniqueness. But then again, what puzzles me was what's the mechanism. And I've seen people also discuss. So one interesting was that magnetism or whatever term of signature break-in is, as the superconductivity sets in.
Yeah, it's a strange thing. Yeah.
So at least I've seen one paper from trying to say.
But if you are
media by see that this itinerant island in the surface, but as of now, I don't really.
I don't think there is a good way you can come up with an explanation for why those two are linked. I mean, we tried something else. We said, well, So you have this coupling between this FFLO-like state, and then you also have it coupled to the magnetic order. Suppose instead that your superconductor spontaneously formed an FFLO state, then it must also induce right away this magnetic order. So we propose that possibility as well. Is that right? And then we have to explain where the FFLO state comes from. It's easy to explain where it comes from if the time reversal is broken already on this anti-fermionic order. It's hard to explain why it comes spontaneously. So that was the issue with that explanation. But it does have the advantage then at TC, magnetism and superconductivity will show up.
Yeah.
So it's
quite puzzling.
it is a puzzle. It really is a puzzle.
Yeah. It's also considering. I remember the Mox experiment also shows similar thing that basically emerge at the same time. So,
But then there's the splitting of the direct cone, which was interpreted as a surface direct cone, and that seemed to exist above the superconductor.
I think so.
Yeah, so it seemed like, okay, there.
Oh, yes, I get the.
Yeah.
Okay, nice. Okay, well, good.
Yeah, thank you. If I may, how about your classification? So
That's also good.
a little bit, but let's take the symmetry.
How was
Yeah, so for the experimentation of where these. So topological classification, surface.
Oh, yeah.
But it was like this. So then what we did is we went to a model to see if we can get Bogdanov surfaces under the conditions that the topological classification says we do.
Yeah, that's me.
And so and then in that case, we just make our lives as simple as possible. We have a spherical make a model that we know has the right symmetry properties, and we pair on that and see what happens. So the spherical is not that. That's on the lattice as well. The lattice adds some extra. Also, those extra things has to do with whether you're in a trim or not. In practice, if you have a Fermi surface, it doesn't typically intersect the trim. And so, as long as you have some generic Fermi surface that's not in any special point in the metric space, it's
unclear, but you'll know this much.
I see. And coming down to this global focus.
We all.
I was.
Everybody wants him to succeed.
Is there a way to? So it sounds like in the superconductors there are some Fermi surfaces.
Well, he's the one that introduced lots of magnets. I know.
Yeah, so. Yeah, so
optical.
the difference is that the total charge carried by the Bogdanov Fermi surface is 0. And so your resistance is. Coherent? If you still have phase coherence, you still have 0 resistance. So the issue way to think about that is you can still have point nodes and line nodes. So you can still have 0 energy quasi-particles. And so, but in those cases, which are surface, right? But still there, your DC resistivity is 0. Of course, your AC resistivity changes, but your DC resistivity.
Yeah, that's when he published the ARL.
Yes, that is also true of Bogdanov surface.
Yeah, the thing that you talked about are. That was exactly okay.
So I think at some point it's interesting.
So hard to find.
Partial Fermi surface. But I was at some point I wasn't sure if it's the same thing. But it sounds like also speaks to a Fermi surface in the superconductor state.
Yeah, probably it's similar.
Yeah, and so I was just ask myself if probably the same. So if I keep dump with distance.
Yeah, so it's not DC resistant. But there are other typical, so mainly, so any other responsive amount will show the pervious surface, but not DC resistance. So
Interesting. How about quantum oscillation?
okay, no quantum oscillation. And so the reason for that is, so you have quantum oscillations, you need basically a single charged particle to travel around your whole pervious surface. Yeah, to do an orbit. Yeah, and that's what leads to quantization of vector. But here on these Bogomolov Fermi surfaces, these are mixtures of particles and holes. And you might be lucky and have some orbit that is purely electronic. Like the only constraint you have is
starting from the upper flank surface.
And so you might have a neck here which is purely electron-like and a corresponding neck which is purely hole-like. So it's not a, so.
That's
the main issue is really in how you can use them. I think they really are.
Transfer one clearly shows signatures.
Yeah. This
That's right, but now you have these low energy particles that will conduct.
Right.
Yeah, so penetration depth will work.
A lot of the typical example of things are.
Yeah, density of states will be finite in the superconductor, so there's a few things.
One is.
Yeah.
All right, thank you. Thank you so much.
No problem, no problem.
Also, thank you for the lecture. I thought that was very nice.
They all know the thank you. This specifies some terms.
I know.
Yes, I do.
Sure, do you wanna go out and grab some coffee? Yeah, sure.
I do have a. Specific question, but I do. Yeah, I do have a question too, but I'll just wait.
Okay, that's.
You do.
I mean, mine was not mine trying to understand your previous position.
And we see that exactly at the level of whole focus, sure. And it never goes. But this guy, actually, you want mine. Now, hybridogrammatic, some which is 6, says that non-theoretical behavior.
Channel, I mean, says, you write down delta
But
one,
it's very hard to go
one times logarithm, plus you do delta 2 times logarithm. Delta 2 is equal
At the same
to
time,
1
maybe
delta
you
2
is slightly smaller.
plus you do delta 1 times.
Right now is kind of.
Write down delta 1 plus delta 2 is equal to delta 1 plus delta 2 times you
If
1 plus.
you have several pockets, I will also try to do kind of this.
What is this?
wall just to see what it
This is
is.
But this is equal to.
Maybe you predict everything minus
Minus interaction.
This is something you can check out. I didn't even do technology to like that.
There's no way you can change time.
Yeah, because this is very cheap for very simple reason.
Right,
It's double
one
interaction.
minus.
So the entire lady behaves as a property.
1 minus delta, minus sine. Times 1 minus.
So this is as cheap as self-consistent borrow person.
And this is your interaction. Why I call it channels? Because if this is not here, but if this is not here and this is here, then you get delta 1 equal to delta.
And then also
This
this
direction. If this is here and this is not here, you get delta 1 equal to minus.
That's a lot for me to change. But I have seen also kind of another posting here, even they don't say non-theoretical. They show you that self-energy behavior следует бытло. Minus EMC is a function of frequency. They say nothing about non-theoretical.
Well, the solver says we find out that when this guy becomes well, the minus sign is done by
No, I'm just saying that
use this for the parameter and checks that you lower the energy by 30. Yeah, we have, if you want to read about this, we have review and actually 2 reviews. These are papers from 10 years ago. with Surab Maiti. If you look at me and Maiti, you'll find that they have two long leads. Look at 7. But 7 one's closer closes.